What if everything you thought you knew about the universe was only part of the story? We look up at the night sky and see countless stars, galaxies, and cosmic phenomena. But beneath that breathtaking display lies something even more extraordinary, a reality that might be actively maintaining its own balance, fine-tuning its own laws, and constantly adjusting to preserve harmony and order. This isn't just a philosophical idea or science fiction fantasy. From the precise numerical values that govern the forces of nature to the vast, elegant structures shaping the cosmos, there are compelling, mysterious hints that our universe operates like an intricate, self-correcting machine. In this video, we're going to explore 26 astonishing patterns that point toward this breathtaking possibility. We'll venture from the subatomic realm, where particles behave in ways that challenge our very notion of reality, out to the farthest reaches of the observable cosmos, where dark energy and cosmic inflation sculpt the fate of everything. Each pattern we uncover, from the mind-bending fine-tuning of physical constants to the eerie synchrony of quantum entanglement, suggests that the universe is not a random accident, but a deeply sophisticated, self-regulating system. It's as though reality itself is equipped with a kind of cosmic thermostat, continually adjusting, rebalancing, and refining to sustain the conditions that allow complexity, life, and even consciousness to emerge. This journey will take us through concepts that have puzzled physicists, inspired philosophers, and captivated curious minds for generations. You'll come away with a new perspective on existence, one where chaos and order aren't opposing forces, but partners in an eternal dance guided by principles we are only beginning to grasp. So settle in, open your mind, and get ready to see the cosmos in a completely new light. What you're about to discover might just change how you see everything, from the atoms in your body to the farthest galaxy spinning silently in the dark. This profound notion of a universe that actively maintains its own balance and order is not a modern invention born from advanced mathematics or particle accelerators. In fact, this concept has deep roots, stretching back thousands of years to the very dawn of human curiosity. Ancient Greek philosophers introduced the idea of the logos, a fundamental principle of order and knowledge that they believed governed the cosmos. This was not seen as a distant, detached God, but rather as an inherent rational structure woven into the fabric of existence itself, a kind of cosmic reason ensuring everything functioned according to a purposeful plan. Similar ideas emerged independently across the globe. In ancient China, the concept of the Tao represented the natural, harmonious order of the universe, a flowing balance between opposing forces like yin and yang. The central teaching was that the universe corrects itself, and that aligning with this natural flow was the path to wisdom. These early thinkers observed the cycles of the seasons, the predictable motions of the stars, and the intricate balance of ecosystems, and they deduced that a principle of self-regulation must be at work. This philosophical thread continued to weave its way through history, finding expression in the scientific revolution. When Isaac Newton formulated his laws of motion and universal gravitation, he revealed a clockwork universe, a cosmos governed by immutable, mathematical laws that seemed to create a stable, predictable system. This was a major step toward a scientific understanding of cosmic self-regulation. Later, the development of thermodynamics introduced the concept of homeostasis to physics, the idea that systems naturally move toward a stable equilibrium. Think of a thermostat maintaining a room's temperature, scientists began to wonder if the universe itself might operate on a similar, grander principle. In the 20th century, this idea exploded with new possibilities thanks to two revolutionary theories: quantum mechanics and general relativity. Quantum physics introduced a bizarre world where probability reigns, yet from this chaos, a definite reality consistently emerges. The very act of observation seems to correct a particle's fuzzy potential into a concrete state, suggesting a participatory kind of regulation. Meanwhile, relativity showed us that space and time are dynamic, curving and flexing in response to matter and energy. Cosmologists applying these theories discovered something astonishing. Our universe appears incredibly fine-tuned for life. If the force of gravity were even slightly stronger or weaker, if the mass of a proton were different by a minuscule amount, stars and planets could never have formed. This remarkable precision, known as the anthropic principle, strongly suggests a cosmos that has somehow calibrated its own constants to allow for complexity and observers. Today, cutting-edge theories like the holographic principle and cosmic inflation are pushing these ideas even further. They propose that our entire three-dimensional universe might be a projection of information stored on a two-dimensional surface, a concept that implies a built-in mechanism for conserving and regulating information. From the philosophical musings of the ancients to the complex equations of modern physicists, the suspicion has remained the same: our reality is not a chaotic accident. It is a system, perhaps the ultimate system, equipped with an innate capacity to balance, adjust, and preserve itself. Understanding this rich historical and scientific background is crucial because it transforms the patterns we'll explore from a collection of strange coincidences into potential clues pointing toward a deep, underlying truth about the nature of existence itself. Now let's dive into the first and perhaps most compelling pattern that hints at a self-regulating cosmos: the astonishingly precise fine-tuning of the fundamental constants of physics. These constants are the fixed numerical values that govern the behavior of the universe at every level, from the subatomic to the cosmic. They are not derived from any deeper theory. They simply are what they are, and they appear to be set with unimaginable precision. Consider the speed of light in a vacuum, designated by the letter c. This value is exactly 299,792,458 meters per second, and it serves as the ultimate speed limit for causality in the universe. If this number were even marginally different, the very structure of spacetime would change, affecting how energy and matter interact across the cosmos. Then there is the gravitational constant, known as Big G, which determines the strength of the force of gravity. This force might feel strong when you try to lift a heavy object, but in reality, it is incredibly weak compared to the other fundamental forces. In fact, gravity is about 10 to the 36 times weaker than the electromagnetic force. This specific weakness is crucial. If gravity were slightly stronger, stars would burn their nuclear fuel at a vastly accelerated rate, causing them to flare up and die out in mere millions of years instead of billions, not nearly enough time for complex life to evolve on orbiting planets. Conversely, if gravity were any weaker, it wouldn't be able to pull enough matter together to ignite stars in the first place, leaving the universe a dark, cold, and lifeless expanse of scattered gas. One of the most dramatic examples of this cosmic fine-tuning is the cosmological constant, which represents the energy density of empty space and is responsible for the accelerating expansion of the universe. The observed value of this constant is so exquisitely small that it has been called the worst prediction in the history of physics. Theoretical calculations suggest it should be around 120 orders of magnitude larger than what we actually measure. If it were even a fraction larger, the repulsive force would have been so powerful that it would have torn apart galaxies, stars, and even atoms moments after the Big Bang, preventing any structure from ever forming. The fact that it is perfectly balanced to allow for galaxy formation, and yet still drive an accelerated expansion, is like winning the lottery 1,000,000,000,000 times in a row. We see this same razor's edge balance in the strong nuclear force, the glue that holds atomic nuclei together. This force must be powerful enough to overcome the intense electromagnetic repulsion between positively charged protons, yet not so strong that it causes all the hydrogen in the early universe to fuse into heavier elements too quickly. If it were just a few percent stronger, hydrogen, the fuel for stars, would be rare. If it were slightly weaker, elements essential for life, like carbon and oxygen, might never form at all. The mass of a proton relative to a neutron is another critical value. If it were different, neutrons could not bind into stable atoms, and the universe would consist of nothing but hydrogen, or would have collapsed back in on itself long ago. Each of these constants exists in a breathtakingly narrow window of viability, a window that allows for galaxies, planets, chemistry, and ultimately, us. This isn't just a lucky break. It points toward a universe that has, in some profound way, selected or corrected its own parameters to create a stable, sustainable, and life-friendly reality. But this incredible fine-tuning of the universe's fundamental dials leads us directly to a monumental question. How did such a perfectly balanced initial setup even come to be? The answer may lie in one of the most powerful ideas in modern cosmology, a dramatic event known as cosmic inflation. Picture the universe in its very first moments, a seething, chaotic, and incredibly dense soup of energy. According to the standard Big Bang model, this infant cosmos should have been riddled with extreme irregularities, like lumps in a poorly mixed batter. These dense knots would have gravitated together, potentially creating a universe dominated by enormous black holes and vast, empty voids, a chaotic and likely lifeless mess. Yet, when we look out into the cosmos today, we see something utterly different. On the largest scales, the distribution of matter and energy is almost unimaginably smooth and uniform. This is the first great puzzle that inflation solves, the horizon problem. The horizon problem asks how parts of the universe that are now billions of light years apart, and which could never have been in contact with each other based on the speed of light since the Big Bang, somehow managed to agree on the exact same temperature and density. It's as if two musicians on opposite sides of the world, who have never met or communicated, began playing the same symphony in perfect harmony. Cosmic inflation provides an elegant solution by proposing that the universe underwent a period of exponentially rapid expansion in the first fraction of a second of its existence. This wasn't just fast expansion, it was a growth spurt so violent that it dwarfed the speed of light itself. In less than a trillionth of a trillionth of a trillionth of a second, a subatomic speck of spacetime was stretched to a size larger than our entire observable universe today. This monumental stretching effectively ironed out all the primordial wrinkles and irregularities, smoothing the energy density to an incredible degree, and ensuring that all regions shared a common origin and temperature before this hyper-expansion began. It was the ultimate cosmic correction, taking a potentially chaotic beginning and sculpting it into a coherent, uniform whole. Inflation also masterfully resolves the flatness problem. The geometry of our universe, according to Einstein's general relativity, is determined by the density of matter and energy within it. Too much density, and the cosmos would be curved into a closed sphere, eventually collapsing in a big crunch. Too little, and it would be an open, saddle-shaped universe, flying apart into eternal cold and darkness. The precise, critical density required for a perfectly flat universe is an incredibly unstable balance, like a pencil standing perfectly upright on its tip. Yet, observations from satellites like Planck show our universe is flat too, within a margin of error of just 0.1%. How did it find this perfect equilibrium? Inflation's tremendous stretching would have flattened the observable universe's geometry in the same way that blowing up a balloon smooths out and flattens any small crinkles on its surface. No matter what the initial curvature was, inflating it to such an enormous degree would force it to appear flat to any observer within it. This isn't just a lucky outcome. It behaves like a built-in feedback mechanism, driving the universe toward this stable, balanced state. The implications of this are profound. It suggests that the universe possesses innate tendencies toward equilibrium and stability, actively working to prevent disorder from taking over. The inflationary correction wasn't a one-time event with permanent results. We see this self-regulating behavior continuing today in the form of dark energy, which fine-tunes the expansion rate, and in the gravitational dance of galaxies that avoids catastrophic collisions. The theory even predicts that while inflation smoothed our observable patch of the universe, it may have ended at different times in different places, giving rise to a vast multiverse of bubble universes, each with potentially different physical laws. In this grander view, inflation acts as a cosmic natural selection mechanism, where only the stable, self-consistent universes that can form galaxies and stars will ever be observed. The incredible uniformity we see in the cosmic microwave background radiation, the afterglow of the Big Bang, is the direct piece of evidence, the fossilized imprint of this primordial corrective process. It stands as a powerful testament to a universe that didn't just start with order, but one that actively and dynamically created that order out of potential chaos. This remarkable fine-tuning, this breathtakingly precise calibration of the universe's dials, forces us to confront a truly profound question: why? Why would the constants of nature be set to such specific values that they allow for stars, planets, and ultimately living, breathing, conscious beings to exist? This is where we encounter our third compelling pattern, the anthropic principle in action. At its heart, this principle presents a simple yet mind-bending observation. We find the universe to be perfectly suited for life because if it weren't, we wouldn't be here to notice. It seems almost too obvious, a mere tautology, but when you really sit with its implications, it begins to look less like a trivial statement and more like a profound clue about the self-selecting, and perhaps even self-correcting, nature of reality itself. Think of it this way: imagine you are a fish born in a pond. You might eventually start to wonder, why is this pond so perfectly suited for me? The temperature is just right for my biology. The water contains exactly the oxygen I need to breathe, and the ecosystem provides my ideal food. A foolish fish might conclude that the pond was meticulously designed just for it. A wiser fish would realize that it is perfectly adapted to the pond because it was born there. It is the product of the pond's conditions. The pond itself may be one of countless bodies of water, each with different temperatures, salinities, and chemistries. The fish can only observe the one it exists in. In this same way, we can only observe a universe that has the necessary conditions for our existence. The mere fact that we are here to take measurements and ask questions automatically filters the kind of universe we can find ourselves in. It must be one that allows for observers. This idea operates powerfully at the grandest cosmic scale. The fine-tuning of gravity, the cosmological constant, and the strong nuclear force are not happy accidents we happen to stumble upon. They are prerequisites for our existence. In a vast multiverse, a seemingly infinite froth of bubble universes, each with its own random set of physical constants and laws, Only a tiny, tiny fraction would have the right recipe to form complex structures and foster life. The overwhelming majority would be stillborn, collapsing instantly or flying apart too fast for atoms to form, or might be dominated by black holes or lack chemistry altogether. We quite necessarily find ourselves in one of the rare habitable bubbles. From this perspective, the universe isn't necessarily fine-tuned for us. We are simply the inevitable product of a universe that is tuned this way. The act of observation itself becomes a selective filter, a form of cosmic natural selection where only life-permitting universes ever get observed. But the anthropic principle's hints at a self-correcting reality become even more intriguing when we descend from the cosmos to the quantum realm. This is where the so-called participatory anthropic principle comes into play, an idea most famously associated with physicist John Archibald Wheeler. He proposed that observers are necessary to bring the universe into being. In the bizarre world of quantum mechanics, particles exist not as definite things, but as clouds of probability, a blur of potential outcomes. It is only through the act of measurement, of observation, that this quantum fog collapses into a single, definite reality. Wheeler's radical suggestion was that this process might be happening on a cosmic scale. In his famous delayed choice thought experiment, he showed how an observer in the present could seemingly influence the past state of a particle, retroactively determining whether it behaved as a wave or a particle billions of years ago. This leads to a staggering possibility that the universe only achieves a concrete, definite history when it is observed by a conscious being. It's as if the universe is in a constant state of potential, a superposition of all possible histories, and it requires an observer to correct it into a single, consistent timeline. The presence of a conscious observer becomes the mechanism that resolves quantum ambiguity into classical reality. This doesn't mean we control the universe with our thoughts, but rather that consciousness and the physical world are deeply intertwined in a feedback loop. The universe creates the conditions for life, and life, through observation, in turn solidifies the universe. It is a continuous process of mutual adjustment, a dance between the observer and the observed that maintains a stable, coherent reality from the quantum soup of possibilities. This pattern powerfully hints that consciousness is not a passive bystander in a predetermined cosmos, but may be an active, fundamental participant in the universe's ongoing project of self-regulation and self-definition. This journey from the cosmic to the quantum, from the fine-tuning of the universe to the participatory role of the observer, brings us to one of the most direct and startling examples of self-correction in nature, the process of quantum decoherence. To understand this, we have to venture into the bizarre and counterintuitive world of the very small, where the rules of our everyday experience completely break down. In the quantum realm, particles like electrons and photons don't exist in a single, definite location with a specific state. Instead, they exist in a blur of all possible locations and states simultaneously, a condition known as a superposition. It's as if a single particle is smeared out across a range of probabilities, only becoming a concrete thing when we finally decide to look at it. This isn't just a theoretical idea. It's been proven time and again through some of the most famous experiments in all of science. The classic demonstration is the double-slit experiment. Imagine a barrier with two thin, parallel slits cut into it. We fire a stream of particles, say electrons, one at a time toward this barrier. On the other side is a screen that lights up wherever an electron hits it. If electrons behaved like tiny bullets, we would expect to see two clusters of dots on the screen directly behind the two slits. But that's not what happens. Instead, as the electrons arrive one by one, they begin to build up an interference pattern, a series of light and dark bands that can only be created by waves overlapping and interacting with each other. This is utterly perplexing. How can a single electron passing through one slit interfere with itself as if it had gone through both slits at the same time? The only conclusion is that each individual electron does not take a single path. It exists in a superposition, effectively passing through both slits simultaneously and interfering with its own potential path. It behaves not as a particle but as a wave of probability. Now, here is where the act of observation performs its strange magic, its act of correction. What happens if we place a detector at one of the slits to determine which path each electron actually takes? The moment we do this, the interference pattern instantly vanishes. The screen now shows only two simple bands, just as if we were firing little bullets. The mere act of measuring, of observing the electron's path, forces it to choose a single reality. It collapses from a fuzzy cloud of possibilities into a definite particle with a known location. This is the heart of the quantum measurement problem. The universe at its most fundamental level seems to remain in a state of multiple potentialities until an interaction, a measurement, occurs to resolve the ambiguity. This process of a quantum system losing its coherence and settling into a single classical state is what physicists call decoherence. It is the mechanism by which the wavy, probabilistic quantum world gives way to the solid, definite reality we experience. This corrective process becomes even more mystifying with a modern variation known as the quantum eraser experiment. This setup adds a twist that seems to play tricks with time itself. Scientists can mark which path a particle takes using a special method, thus destroying the interference pattern just like before. But then, they can arrange things so that this which path information can be erased after the particle has already hit the final screen. Astonishingly, if this information is erased, the interference pattern miraculously reappears in the data. It's as if the particle's decision on whether to behave as a wave or a particle is retroactively changed by an action that happens in its future. This doesn't mean we can send messages back in time, but it profoundly challenges our classical notion of a linear, deterministic chain of cause and effect. It suggests that the universe holds onto quantum possibilities until the very last moment, constantly adjusting and finalizing outcomes based on the total context of observation and interaction. So, what causes this collapse? What is the nature of this observation that corrects quantum potential into classical reality? This is one of the biggest open questions in physics. Some interpretations suggest it is the interaction with a macroscopic measuring device that causes decoherence. Others, in the spirit of the Copenhagen interpretation, argue that it requires a conscious observer. The most widely accepted view today involves decoherence through environmental interaction. A lone quantum system can maintain its superposition, but the moment it interacts with even a single photon or air molecule from its environment, it becomes entangled with that environment. This entanglement spreads the quantum information out so widely and so quickly that the superposition is effectively lost for all practical purposes, and a single outcome is selected. From this perspective, the universe is in a constant, frenetic dance of measurement. Every interaction, every collision between particles, every photon bouncing off an object is a tiny act of observation, a miniature measurement event that continuously resolves quantum uncertainty. This paints a picture of a reality that is not static but is perpetually being crystallized into existence through an unimaginably vast network of interactions. It is a self-correcting system of the most fundamental kind, where the simple act of things touching each other, of information being exchanged, is what maintains the consistent and reliable world we perceive around us. Yet this relentless march toward chaos presents us with a profound cosmic paradox. If the universe is inevitably sliding into a state of maximum disorder, how do we explain the breathtaking complexity and intricate structure we see everywhere? From the majestic spiral arms of galaxies to the delicate double helix of DNA, the cosmos is teeming with organized systems that seem to defy the second law. This is our fifth compelling pattern: the universe's remarkable ability to create localized pockets of order, temporary victories against the tide of entropy that allow for stars, planets, and life to flourish. It's as if the cosmos is engaged in a constant balancing act, a self-correcting dance where pockets of chaos are harnessed to build even greater complexity. To understand this, we need to reframe our view of entropy. The second law doesn't forbid local decreases in disorder. It only states that the total entropy of a closed system must increase. This creates an opening, a loophole of sorts. A system can indeed become more orderly, but only if it exports entropy elsewhere, effectively paying for its internal organization by creating even greater disorder in its surroundings. A simple, everyday example is your home refrigerator. Inside the fridge, things get colder and more ordered as heat is removed. But this doesn't violate the second law because the refrigerator's motor is working hard, consuming electrical energy and expelling even more waste heat into your kitchen. The local order inside the fridge is purchased by increasing the overall entropy of your kitchen, and by extension, the universe. This is the fundamental trade-off that powers the emergence of all complexity. Now scale this idea up to a cosmic level. The most dramatic example of this entropy export is a star. A star like our Sun is a masterpiece of localized order, a massive, self-gravitating sphere of incandescent plasma, maintaining a stable nuclear fusion reaction for billions of years. It is a highly organized system, yet it is constantly generating enormous entropy through the radiation it emits out into the cold depths of space. Every photon that leaves the Sun's surface carries away a tiny bit of disorder, allowing the star to maintain its intricate internal structure. This process is the engine of creation for the entire universe. Without stars acting as these colossal entropy-exporting engines, the primordial hydrogen and helium from the Big Bang would have remained a cold, thin, and utterly simple gas, forever lost to the final heat death. Instead, stars use gravity to create intense pressure and heat, forging heavier elements in their cores and then, in their spectacular deaths as supernova, scattering those complex atoms across space. This stellar alchemy is the ultimate act of cosmic self-correction, taking a uniform, featureless early universe and seeding it with the raw materials for planets, oceans, and life. This beautiful interplay is perhaps most perfectly embodied in a black hole. For decades, black holes were thought to be the ultimate paradox, cosmic vacuum cleaners that simply destroyed matter and information, seemingly violating the laws of thermodynamics. Then, physicist Stephen Hawking made a revolutionary discovery: black holes aren't black at all. Due to quantum effects at their event horizons, they slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation carries entropy away from the black hole, and it turns out that a black hole's entropy is directly proportional to the surface area of its event horizon, not its volume. This was a stunning revelation. It suggests that all the information about what fell into the black hole is somehow encoded on its two-dimensional boundary. A black hole is not a destroyer of order but a system that manages information and entropy in the most efficient way physically possible. It represents an extreme state of equilibrium, a natural endpoint for entropy that still somehow preserves the universe's informational structure, hinting at a deep, self-regulating principle even in the most extreme environments. And finally, we see this pattern culminate in life itself. Every living organism is a stunning rebellion against disorder. A human body is infinitely more complex and ordered than the random assortment of atoms in the food we eat and the air we breathe. We maintain a constant internal temperature, repair damaged cells, and build intricate structures like bones and neural networks, all while constantly fighting off the decay that the second law demands. How is this possible? Biology solves the entropy problem through an endless cycle of energy consumption. We are open systems, continuously taking in high-quality, low-entropy energy from the sun, stored in plants or animals, and using it to power our internal processes. In return, we expel waste heat and chemical byproducts, which are in a much more disordered state. We are, in essence, local eddies in the great river of entropy, temporarily creating and sustaining islands of exquisite complexity by directing the flow of disorder outward. From the nuclear furnace of a star to the metabolic engine of a cell, the universe demonstrates a pervasive tendency to create and sustain order, not as an exception to the rules, but by working within them, constantly correcting and balancing itself to write a more interesting story than a simple slide into silence. This breathtaking cosmic cycle of entropy and order finds its most beautiful and tangible expression in the very fabric of the galaxies themselves. Look up at the Milky Way on a clear night, and you're not just seeing a static collection of stars, you're witnessing a vast, dynamic, and incredibly efficient recycling plant operating on a grand scale. Galaxies are not permanent structures but are instead engaged in a continuous loop of creation and destruction, a process that takes the simple ashes of the early universe and forges them into the complex ingredients necessary for planets and life. This is our sixth profound pattern, galactic recycling, a self-sustaining mechanism that ensures the raw materials of creation are never wasted but are perpetually repurposed to build new worlds. It all begins with the first generation of stars, often called population 3 stars. These giants were born from the pristine hydrogen and helium that emerged from the Big Bang. They contained none of the heavier elements, what astronomers call metals, that are so common today. Without these elements to help radiate heat away, these first stars could grow to be monstrously large, hundreds of times the mass of our Sun. Their immense size meant they lived fast and died young, burning through their nuclear fuel in just a few million years. But their spectacular deaths were not an end. They were the essential first step in seeding the universe with complexity. When these behemoths reached the end of their lives, they did not fade quietly. They exploded as cataclysmic supernova, events so powerful they briefly outshine entire galaxies. Within these unimaginable furnaces of pressure and energy, the simple nuclei of hydrogen and helium were fused together into every element on the periodic table up to iron. The incredible force of the explosion itself then forged elements even heavier than iron, like gold, silver, and uranium. In their final moments, these first stars performed the universe's most crucial act of alchemy, scattering their enriched guts across vast clouds of interstellar gas. They took a simple, metal-poor universe and corrected it, injecting it with the very stuff of planets and biology. This process of stellar enrichment didn't stop with the first stars. It's a cycle that continues in our own galaxy today, driven by different types of stellar deaths. Lower mass stars like our Sun contribute in a more gentle but equally vital way. They may not go supernova, but in their old age they become red giants and shed their outer layers into space, forming beautiful, glowing shells of gas known as planetary nebulae. These gossamer clouds are rich with carbon, nitrogen, and oxygen, the fundamental building blocks of life as we know it. Then there are the neutron star mergers, arguably the universe's most spectacular jewelry stores. When two ultra-dense remnants of dead stars spiral into each other and collide, the event ripples spacetime itself with gravitational waves and creates a kilonova, an explosion that manufactures staggering amounts of heavy elements like gold, platinum, and plutonium in a matter of seconds. A single such event can seed an entire galaxy with enough gold to gild every planet in 1,000 solar systems. Each of these cosmic events, the violent supernova, the gentle planetary nebula, the cataclysmic neutron-star merger, acts as a corrective mechanism. They prevent the universe from stagnating as a thin soup of hydrogen, instead constantly churning and enriching the interstellar medium with each successive generation of stars. This enriched gas doesn't just float away into nothingness. Gravity, the great architect of the cosmos, pulls these heavy element-laden clouds together into massive molecular clouds, cosmic nurseries that can span light years. Within these dark, dusty wombs, the recycled material from long-dead stars begins to collapse under its own weight, fragmenting into clumps that will ignite as new stars. And this time, because the gas cloud is peppered with heavy elements, the story is different. The dust grains act as nucleation sites, helping the gas to cool and collapse more efficiently. They also clump together to form rocky planets in orbiting disks around these newborn stars. The carbon, oxygen, iron, and silicon forged in a stellar explosion billions of years ago may now become part of an asteroid, a mountain range on a distant world, or even a living cell. Our own solar system is a product of this recycling process. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all created in the heart of a massive star that died in a supernova explosion over 5 billion years ago. We are literally made of stardust, the recycled remains of a celestial ancestor. This isn't just a poetic metaphor, it's a physical reality that points to a universe fundamentally geared toward renewal. It ensures that the death of one star is never a true end, but merely a transformation, a necessary step in an eternal cycle that constantly corrects and replenishes the cosmic inventory, perpetuating the possibility of complexity and life across billions of years and countless star systems. Just as the universe masterfully recycles its material to build new worlds, it also seems to possess a mysterious governor for its own expansion, a hidden hand ensuring the entire cosmic engine doesn't fly apart or collapse in on itself. This brings us to one of the most profound and puzzling discoveries in modern cosmology: dark energy. For much of the 20th century, astronomers believed the universe's expansion, born from the Big Bang, was gradually slowing down. It seemed logical. The gravitational pull of all the matter in the cosmos, every galaxy, every star, every speck of dust, should be acting like a cosmic brake, tugging on the fabric of spacetime and decelerating the great outward rush. The big question was whether this gravitational pull was strong enough to one day halt the expansion entirely and reverse it, leading to a catastrophic big crunch where all of reality collapses back into a singularity. Then, in the late 1990s, two independent teams of researchers made a discovery that turned this entire picture on its head. By meticulously observing distant supernova, exploding stars that serve as standard candles for measuring cosmic distances, they made a shocking revelation. The universe's expansion wasn't slowing down at all. It was speeding up. It was as if everyone on Earth threw a ball into the air expecting it to fall back down, only to watch in astonishment as every single ball shot away into the sky faster and faster. This was a paradigm-shifting moment that demanded a radical explanation. Something was out there, a mysterious something permeating the vacuum of space itself, exerting a repulsive force that counteracts gravity's attractive pull. This something was given a name that reflects our profound ignorance of its true nature: Dark energy. The leading theoretical candidate for dark energy is the cosmological constant, an idea first proposed by Albert Einstein and later discarded by him as his greatest blunder. This isn't a blunder at all, but a concept that has made a triumphant return. The cosmological constant is essentially the energy intrinsic to empty space itself. According to quantum physics, a perfect vacuum isn't truly empty. It's a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum jitter endows every cubic centimeter of nothingness with a tiny amount of energy. Einstein's equations show that this energy would have a very strange property. It would cause space-time to repel itself, leading to an accelerated expansion. The problem, however, is one of scale. When physicists try to calculate the predicted strength of this vacuum energy based on quantum theory, they arrive at a number that is a staggering one, followed by 120 zeros times larger than what we actually observe. This is the worst prediction in the history of science, a discrepancy so vast it tells us we are fundamentally missing a crucial piece of the puzzle. Yet the value we do measure is exquisitely, delicately perfect. If dark energy were significantly stronger, the accelerated expansion would have ripped apart galaxies before they could even form. If it were any weaker, gravity would have long since pulled the universe back into a fiery collapse. Its precise value seems to be another example of incredible cosmic fine-tuning, acting as a perfect counterbalance to the force of gravity. This is where dark energy reveals its role as a profound cosmic corrective mechanism. It appears to be the universe's built-in safety valve against gravitational collapse. Without it, the fate of the cosmos would be a grim battle between expansion and contraction, likely ending in that total collapse or a slow, cold fade into darkness. Instead, dark energy ensures a more stable, long-term evolution. By maintaining a specific rate of acceleration, it prevents a big crunch while also ensuring the expansion doesn't become so violently rapid that it tears the fabric of spacetime apart in a big rip. It provides a dynamic equilibrium, a balancing force that allows large-scale structures like galaxy clusters to hold themselves together through gravity, even as the space between these clusters expands at an ever-increasing rate. This isn't a static balance but a dynamic one, a carefully maintained tension between two opposing forces that has allowed the universe to persist for billions of years and develop the complexity we see today. Dark energy, in this light, is not a destructive force but a preservative one, a fundamental feature of spacetime itself that actively works to regulate the cosmos's expansion and ensure its longevity, acting as the ultimate governor on the engine of creation. While the universe masterfully regulates its expansion through dark energy, it also performs an equally delicate balancing act at the smallest scales, governing the very mass of the fundamental particles that make up everything we see and touch. This brings us to the eighth astonishing pattern, the role of the Higgs field and its incredible fine-tuning for mass regulation. To grasp the profound significance of this, we need to venture into the subatomic world and understand a revolutionary idea: that empty space is not truly empty. Instead, it is filled with an invisible, energetic field that permeates every corner of the universe, the Higgs field. Think of it not as a field of force like magnetism, but more like a cosmic molasses or a vast, invisible ocean that all particles must move through. The genius of this mechanism lies in its interaction with different particles. Particles that interact strongly with the Higgs field, like the top quark, move through this cosmic molasses with great difficulty. They become heavy and sluggish. Particles that interact only weakly, like photons, zip through completely unimpeded. They remain massless and travel at the speed of light. The electron, a fundamental building block of atoms, has just the right amount of interaction to give it a specific, crucial mass. This is not a random process. The specific value of the Higgs field, its energy level throughout the universe, is what sets the masses for all these fundamental particles. And this value is not something dictated by any other known law of physics. It is a fundamental constant of nature, and it appears to be set with mind-boggling precision. The consequences of even a tiny deviation in this value are nothing short of catastrophic for any possibility of a complex universe. Let's play out two scenarios. First, imagine if the Higgs field were significantly stronger than it is. In this universe, the cosmic molasses would be far more viscous. Particles would interact with it much more intensely, leading to dramatically increased masses for all fundamental particles. Electrons would become incredibly heavy. This would have a domino effect on the structure of atoms. Heavy electrons would spiral into the atomic nucleus almost instantly, making stable atoms impossible. Without stable atoms, there can be no chemistry. Without chemistry, there can be no molecules, no planets, no stars, and certainly no life. The entire universe would consist of a boring, featureless soup of collapsed matter. Now consider the opposite scenario, a universe where the Higgs field is significantly weaker. In this reality, the field's value would be lower, making the cosmic molasses much thinner. Particles would interact with it only very weakly, resulting in most particles having little to no mass. Electrons would be almost massless. While this might sound less destructive, it would be equally fatal to complexity. In such a universe, the delicate balance that allows atoms to form would be shattered. The behavior of matter would be radically altered, likely preventing the formation of the diverse elements we see in our periodic table. Stars might not be able to ignite or sustain nuclear fusion in a stable way. The universe would remain a simple, cold place, devoid of the intricate structures that arise from having particles with a specific, stable set of masses. This incredible fine-tuning points directly toward a self-correcting or self-selecting principle. The specific value of the Higgs field seems to be chosen from a nearly infinite range of possibilities to allow for a very specific outcome, a universe that can support atomic structure and complexity. It acts as a cosmic regulator, ensuring that the masses of particles are not arbitrary, but are precisely calibrated to enable the existence of everything from hydrogen atoms to human beings. The discovery of the Higgs boson in 2012 at the Large Hadron Collider was a monumental confirmation that this field exists, but it did not explain why its value is what it is. That remains one of the deepest mysteries in physics. The Higgs mechanism doesn't just give particles mass, it provides the stable foundation upon which the entire architecture of our reality is built. A foundational parameter that the universe itself appears to have carefully set and maintained to guarantee its own stability and richness. If you could see the universe with eyes sensitive to microwave radiation, the entire sky would glow with a faint, almost perfect uniform light. This is the cosmic microwave background, the oldest light in existence, a fossilized snapshot of the universe when it was a mere 380,000 years old. It is the afterglow of the Big Bang itself, cooled and stretched by 14 billion years of expansion into the microwave part of the spectrum, and its most breathtaking feature is not its age but its incredible smoothness. From every direction we look, this primordial light arrives with a nearly identical temperature of about 2.7 degrees above absolute zero. The variations, or anisotropies, in this temperature are almost absurdly tiny fluctuations of less than 1 part in 100,000. To put that in perspective, that's like looking at a perfectly smooth marble the size of Earth and finding the tallest mountain is only about 200 feet high. This extreme uniformity is not what you would expect from a violent, explosive birth. It is the signature of a universe that has undergone a profound and dramatic act of correction, a smoothing process of epic proportions. This incredible smoothness presented cosmologists with a major puzzle known as the horizon problem. The cosmic microwave background light coming from opposite sides of the sky has the same temperature to that astonishing precision. But here's the catch. According to the standard Big Bang model, these two regions on opposite sides of the observable universe were never in causal contact with each other. They were separated by a distance greater than light could have possibly traveled in the mere 380,000 years since the universe began. It's as if you walked into a vast, crowded room and found that every single person, even those on opposite sides who have never met or communicated, are all wearing exactly the same outfit down to the tiniest thread. Without some way to coordinate, this perfect matching is impossible. The universe, it seemed, had a secret it wasn't telling. How could regions that were effectively strangers to one another have agreed on such a precise thermal equilibrium? The solution to this enigma is one of the most powerful validations of cosmic inflation theory. Inflation proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of hyper-exponential expansion, inflating from a subatomic speck to a volume larger than our entire observable universe in less time than it takes light to cross a proton. This wasn't just fast growth, it was a stretching of spacetime itself so violent that it effectively took a tiny, primordial patch of the universe that was in thermal equilibrium, a patch where every part had been in contact with every other part, and blew it up to become everything we can see today. The entire observable cosmos from one end to the other was once a single, infinitesimally small and perfectly uniform region. Inflation then took that uniformity and stamped it across the entire sky. It is the ultimate ironing out mechanism, smoothing any primordial wrinkles and ensuring that the universe we observe started with a nearly flawless, even temperature. The cosmic microwave background is the direct evidence of this monumental corrective event, a frozen moment in time that captures the stunningly smooth result of inflation's work. But the story doesn't end with perfect smoothness. Those tiny 1 part in 100,000 fluctuations are arguably even more important than the uniformity itself. They are the universe's original imperfections, the seeds from which all cosmic structure would grow. Without them, the universe would be a vast, featureless, and boring sea of gas. Gravity needs something to work with, a slightly denser region to begin pulling matter together. These minuscule temperature variations correspond to tiny differences in density in the early universe. The slightly warmer spots are regions where matter was a tiny bit more densely packed. The cooler spots were slightly more empty. Inflation theory not only explains the overall smoothness, but also provides a compelling origin for these crucial fluctuations. It proposes they were born from quantum fluctuations, the same seething, probabilistic energy of empty space we see today, that were caught and magnified to cosmic size by the rapid inflationary expansion. What were once random quantum jitters on a subatomic scale were stretched into macroscopic density variations that span the cosmos. This is a profoundly self-correcting process in action. The universe didn't just achieve a bland, featureless equilibrium. It achieved a dynamic equilibrium. It smoothed itself out to an incredible degree, preventing a chaotic, lumpy disaster, but it also intelligently preserved and even created from quantum noise the exact right kind and magnitude of imperfections needed for the next chapter of its story. These tiny seeds were the perfect size. If the fluctuations had been much smaller, gravity would have been too weak to overcome the expansion of the universe, and no galaxies or stars would ever have clumped together. If they had been much larger, matter would have collapsed into enormous, universe-spanning black holes far too early. Instead, the fluctuations were exquisitely tuned to allow for the gradual, graceful formation of the cosmic web, the vast filaments of galaxies and great voids that structure the universe today. The cosmic microwave background, therefore, is far more than a relic. It is a blueprint. It shows us a universe that actively corrected its own initial conditions, not to create perfection, but to create potential. It established a stable, uniform foundation while simultaneously planting the delicate seeds of future complexity, demonstrating a breathtaking capacity for self-regulation on the very largest scales imaginable. While the vast scales of cosmic expansion and the subatomic world of quantum fields reveal profound fine-tuning, we find this same principle of self-correction operating right here in our own celestial backyard. Our solar system is a mesmerizing dance of planets, moons, and asteroids, all whirling around the Sun in a complex gravitational ballet that has remained remarkably stable for over 4 billion years. At first glance, this might not seem surprising. After all, the planets simply follow the elegant curves of space-time dictated by the Sun's gravity. But when you look closer, this enduring harmony is a mathematical miracle. The solar system is not a static, clockwork mechanism. It is a dynamic and chaotic gravitational arena where every single body tugs on every other. Left unchecked, these countless tiny perturbations should have sent planets careening into each other or flung them out into interstellar space long ago. The fact that this hasn't happened points to a hidden layer of celestial mechanics, a set of self-correcting mechanisms that actively maintain this long-term orbital peace. One of the most fascinating tools in this cosmic stabilization toolkit is the concept of Lagrange points. Named after the mathematician Joseph Louis Lagrange, these are 5 specific points in the orbital vicinity of any two large bodies, like the Sun and a planet, where the gravitational and centrifugal forces perfectly balance. At these special locations, a smaller object can essentially park itself and orbit in a stable lockstep with the larger bodies. The most famous of these, L4 and L5, are naturally stable zones, gravitational valleys where matter tends to collect and be protected. We see this in action with the Trojan asteroids, which orbit the Sun in the same path as Jupiter, clustered around its L4 and L5 points. These points act as cosmic shepherds, safely corralling potential debris that might otherwise become hazardous projectiles, preventing them from destabilizing the orbits of the inner planets. It's as if the solar system has built-in gravitational parking spots that help to manage traffic and avoid collisions. Even more dynamic are the phenomena of orbital resonances. This occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other because their orbital periods are related by a ratio of small whole numbers. A perfect example is the resonance between Neptune and Pluto. For every 2 orbits Neptune completes around the Sun, Pluto completes exactly 3. This rhythmic gravitational dance ensures they never get too close to each other, preventing a catastrophic interaction that could eject tiny Pluto from its orbit. We see this same principle stabilizing the gaps in Saturn's rings, where the gravitational pull of the planet's moons clears out particles that would naturally fall into these resonant orbits. It's a beautiful, self-perpetuating feedback loop. The gravitational interactions create a rhythm, and that very rhythm then moderates the interactions, preventing them from becoming disruptive. The system is constantly tuning itself, like a master pianist gently adjusting the tension on the strings to maintain perfect harmony. The story of planetary migration adds another layer to this narrative of self-regulation. We now believe that the giant planets in our solar system were not born in their current positions. Early in the solar system's history, gravitational interactions with the vast disk of gas and planetesimals likely caused Jupiter, Saturn, Uranus, and Neptune to migrate inward and then outward. This grand tack, as it's called, could have been a period of tremendous instability. Yet, instead of triggering chaos, it may have been a crucial corrective phase. The migration of these giants is thought to have sculpted the inner solar system, potentially clearing out debris and helping to establish the well-spaced, stable orbits of the terrestrial planets like Earth and Mars. The system experienced a period of dramatic adjustment, but through the complex interplay of gravitational forces, it settled into a new, even more stable configuration. This suggests that the solar system isn't just statically stable. It possesses a kind of resilience, an ability to undergo significant changes and still find its way back to a balanced state. This inherent tendency toward gravitational equilibrium isn't unique to us. As we discover thousands of exoplanetary systems around other stars, we see a stunning variety of configurations: hot Jupiters orbiting close to their stars, tightly packed systems of super-Earths, and worlds in wildly eccentric paths. Yet, even in these alien arrangements, we find evidence of the same balancing acts through resonances and migration. This points to a universal principle: complex gravitational systems, when left to their own devices, naturally evolve toward states of long-term stability. They possess built-in corrective feedback mechanisms that dampen chaos and encourage harmony. Our solar system's 4.5 billion years of peaceful coexistence is not a fortunate accident but a testament to this deep-seated cosmic tendency. It shows that the same drive for balance that we see in the fine-tuning of constants and the smoothing of the early universe is also woven into the very fabric of orbital mechanics, ensuring that islands of order can persist and flourish amidst a cosmos of potential chaos. This incredible stability we see in our solar system, a delicate gravitational dance maintained over billions of years, finds a stunning parallel right here on Earth in the dynamic, ever-changing tapestry of life itself. The cosmos may correct its orbits and constants, but biology performs its own act of real-time adjustment on a scale we can directly observe. Life on Earth is not a static masterpiece. It is a relentless, iterative process of trial and error, a system that constantly corrects and refines itself in response to a shifting environment. This is biological evolution, and it stands as one of the most powerful examples of self-regulation we can find, a microcosm of the larger balancing acts seen throughout the universe. At its heart, evolution is a feedback loop of breathtaking simplicity and power. The mechanism is driven by random genetic mutations, tiny, accidental changes in an organism's DNA. Most of these changes are neutral or harmful, but every so often, a mutation provides a slight advantage. Perhaps it allows a beetle to digest a new type of leaf, or a bird to have a slightly more efficient wing shape. In a stable environment, this advantage might not mean much. But when the environment changes, a new predator arrives, the climate shifts, a food source disappears, this small advantage becomes everything. The individuals with the beneficial trait are more likely to survive, thrive, and most importantly, reproduce. They pass this successful genetic correction on to their offspring. Over generations, this process, known as natural selection, acts like a slow, steady pressure, guiding the entire population toward a better fit with its surroundings. The environment presents a problem, and life, through this blind, algorithmic process, works to find a solution. It is a system that learns from its mistakes, constantly editing the genetic code of species to maintain their place in the world. We can see this self-correcting power in action all around us, sometimes with alarming speed. The rise of antibiotic resistance in bacteria is a classic and sobering example. When we introduce an antibiotic into a population of bacteria, it acts as a powerful new environmental pressure. The drug wipes out the vast majority of the bacterial cells. But within that massive population, a few individuals might randomly possess a genetic mutation that makes them slightly less susceptible to the drug. They survive the onslaught. These few resistant bacteria then multiply, passing their resistance genes to the next generation. Very quickly, the entire bacterial population can become resistant, rendering the antibiotic useless. The medical community is then forced to correct its own strategy, developing new drugs to counter the bacteria's new adaptation. This is an arms race driven by evolution's relentless corrective pressure, demonstrating how life constantly adjusts to overcome threats and maintain its existence. On a grander scale, we see this same process leading to the magnificent diversity of life through speciation events. Imagine a single species of bird living on a mainland. Some individuals get blown by a storm to a distant island. This new environment has different food sources, different predators, and different competitors. The isolated population faces a new set of challenges. Over thousands of generations, natural selection corrects the island population's trajectory to better suit this new home. Perhaps their beaks gradually change shape to crack open a different type of seed. Their plumage might shift in color for better camouflage against the island's foliage. Eventually, the island birds become so different from their mainland ancestors that they can no longer interbreed. They have become a new species. This process, repeated countless times across millions of years and in countless environments, is how a single ancient life form corrected and diversified itself into the incredible array of creatures we see today, from deep-sea anglerfish to towering redwood trees. Each species represents a successful, time-tested solution to the problem of survival in a particular niche. Perhaps the most elegant evidence of evolution's corrective power is the phenomenon of convergent evolution. This occurs when completely unrelated species, facing similar environmental challenges in different parts of the world, independently arrive at nearly identical solutions. The streamlined, torpedo-like body shape of a shark, a dolphin, and an extinct marine reptile called an ichthyos is a perfect example. Sharks are fish, dolphins are mammals, and ichthyosaurs were reptiles. They evolved on entirely separate branches of the tree of life. Yet, the common problem of moving efficiently through water led natural selection to correct their forms toward the same optimal shape. We see the same thing with the wings of birds, bats, and insects. The genetic instructions are different, but the functional outcome is the same. This tells us that evolution is not a random walk. It is a process that converges on effective solutions. The environment poses a question, and life, through the blind, mechanical process of mutation and selection, finds a way to answer it, often arriving at the same brilliant answer multiple times. This mirroring of cosmic patterns is profound. Just as the universe seems to fine-tune its physical constants for stability, and galaxies recycle their materials for longevity, life on Earth fine-tunes its forms and functions for survival. It suggests a universal principle at work, a deep-seated tendency for complex systems to self-organize, to adapt, and to find balance amidst change. Biology shows us that the drive for correction isn't just a feature of the cosmos, it is the very engine of creativity and persistence on our planet. But if life itself is a testament to nature's incredible capacity for self-correction, then the tool we are using to observe it, our own consciousness, may be the most profound corrective mechanism of all. This brings us to a pattern that sits at the very frontier of science and philosophy, a concept that challenges our most basic assumptions about reality itself. The act of observation, the simple fact of being aware, might not be a passive process of receiving information from the world, but an active, participatory force that helps to shape the world into being. This is the startling implication of the 12th pattern, where consciousness and reality perception appear to be locked in a self-regulating dance, a continuous feedback loop where the mind and the cosmos co-create each other. This idea finds its most concrete and most baffling expression in the heart of quantum mechanics. For decades, the double-slit experiment has stood as the quintessential demonstration of quantum weirdness. As we've discussed, particles like electrons behave as probability waves when not observed, existing in a superposition of multiple states and creating an interference pattern. But the very instant a measurement is made to determine which path the particle takes, this wave-like behavior vanishes. The particle collapses into a definite state, a single point in space, and the interference pattern disappears. The critical and deeply mysterious question is, what exactly constitutes a measurement? When does this collapse occur? Is it the interaction with a sophisticated laboratory detector, or does it require something more, the awareness of a conscious observer? This is the heart of the famous measurement problem, and it has led some of the greatest minds in physics to propose that consciousness itself is the fundamental agent that resolves quantum uncertainty into the concrete reality we all share. This radical viewpoint was most famously championed by the Nobel laureate Eugene Wigner. In his thought experiment known as Wigner's Friend, he pushed the implications of quantum theory to their limit. Imagine a physicist, let's call her Alice, inside a sealed laboratory performing a quantum experiment on a particle in a superposition. She sees a definite result. The wave function has collapsed for her. Now, Wigner himself is outside the lab, according to the strict rules of quantum mechanics, until he opens the door and asks Alice for the result. The entire laboratory, including Alice, her equipment, and the particle, must be described as being in a superposition of all possible outcomes. From Wigner's perspective, Alice is in a blurred state of having seen all possible results simultaneously. It is only the act of his conscious observation that collapses the entire system into one consistent history. This thought experiment suggests that consciousness is not merely a product of the brain's biochemistry, but may be a fundamental feature of the universe, a necessary ingredient for translating possibility into actuality. The universe, in this view, exists in a state of pure potential until it is observed by a mind, which performs the ultimate act of correction by selecting a single, consistent timeline from the myriad possibilities. This concept resonates powerfully with ideas found far beyond the physics laboratory, echoing through ancient philosophical and spiritual traditions. The philosophy of idealism, espoused by thinkers like George Berkeley, argues that reality is fundamentally mental, that all that exists are minds and their experiences. The physical world is merely the content of perception. In the East, traditions like Advaita Vedanta Hinduism and certain schools of Buddhism have long taught that the perceived world of separate objects is an illusion or maya, and that the underlying nature of reality is a unified, conscious field from which all things arise. The modern quantum consciousness hypothesis seems to be a scientific cousin of these ancient ideas, proposing that mind is not an emergent property of matter, but that matter is an emergent property of a deeper conscious ground. From this perspective, the universe isn't just observed, it is performed through observation. Our individual consciousnesses are not isolated spectators, but are localized expressions of a universal consciousness, each of us participating in a grand, collaborative process of reality building. constantly correcting the quantum fuzziness into the shared, stable world we navigate every day. This paints a picture of existence not as a pre-recorded movie we are watching, but as an improvisational play that we are all writing together, moment by moment, through the very act of paying attention. But this profound interplay between consciousness and the quantum world, this dance of observation that seems to crystallize reality, leads us to one of the most extreme and mind-bending environments in the cosmos, a place where the very laws of physics are pushed to their breaking point. The black hole has long been the ultimate paradox, a cosmic vault that seemingly locks information away forever, challenging our most fundamental beliefs about how the universe operates. At the heart of this puzzle is a principle so sacred in physics that its potential violation sent shockwaves through the scientific community: the principle of information conservation. In our everyday world, this seems obvious. If you burn a book, it appears the information is lost in the smoke and ash. But in theory, if you could track every single particle and measure its properties with infinite precision, you could, in principle, reverse the process and reconstruct the book. The information is not destroyed, it is merely scrambled. It is always conserved. For decades, black holes presented a terrifying exception to this rule. According to Einstein's general relativity, a black hole is defined only by its mass, electric charge, and spin. It doesn't matter if it formed from a collapsed star, a giant cloud of gas, or a collection of encyclopedias. All that detail, that information about what fell in, is utterly lost behind the event horizon, erased from the universe. This became known as the no-hair theorem. Black holes have no distinguishing features, no hair to tell them apart. The problem was magnified by Stephen Hawking's groundbreaking discovery that black holes are not entirely black. They slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation, however, was calculated to be purely thermal, a random and featureless glow. It contains no information whatsoever about what was inside the black hole. So, when the black hole finally evaporates completely, all the information about everything that ever fell into it would vanish from the universe forever. This apparent destruction of information was a direct violation of quantum mechanics, which insists that information must be preserved. This clash between our two most successful theories of reality became known as the black hole information paradox, and it suggested a deep flaw in our understanding of the cosmos. The resolution to this paradox is pointing toward one of the most profound self-correcting mechanisms imaginable. The universe, it seems, has a built-in failsafe to prevent information loss, a cosmic principle that ensures no detail is ever truly erased. One of the most revolutionary ideas to emerge from this debate is the holographic principle. This astonishing concept proposes that all the information describing a three-dimensional volume of space, like the interior of a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Think of it like a hologram where a three-dimensional image is stored on a flat, two-dimensional piece of film. In this view, when matter falls into a black hole, its information isn't lost inside. It is smeared and stored on the surface of the event horizon in unimaginably tiny Planck-scale pixels. As the black hole emits Hawking radiation, this process is not random. The radiation subtly interacts with this encoded information on the horizon, and over the incredibly long evaporation process, it gradually and meticulously leaks all the information back out into the universe. The black hole doesn't destroy information. It scrambles it and eventually returns it, like a cosmic hard drive that reformats itself but never truly deletes the data. This ensures that the universe always retains a complete record of its history, preserving causal consistency across all of spacetime. Another radical proposal born from this paradox is the firewall hypothesis. If information is to be saved, some physicists argued, then the event horizon cannot be the smooth, uneventful gateway described by Einstein. Instead, it must be a seething, violent wall of high-energy particles, a firewall that instantly incinerates anything crossing it. This drastic idea suggests that the principle of information conservation is so fundamental that the laws of physics must radically change at the horizon to protect it, effectively sacrificing the smoothness of spacetime to save quantum mechanics. While the firewall remains highly controversial, its very existence as a theory highlights the extreme lengths to which physics must go to resolve the paradox. It underscores that information conservation is not a minor rule but a foundational pillar of reality, one that the universe will enforce through seemingly bizarre and extreme mechanisms. Recent advances, particularly in the study of quantum entanglement and wormholes, are providing even more elegant solutions. The ER equals EPR conjecture, an idea proposed by physicists Juan Maldacena and Leonard Susskind, suggests a beautiful duality. Wormholes, also known as Einstein-Rosen bridges, could be the geometric manifestation of quantum entanglement between particles. This implies that the particles emitting Hawking radiation outside the black hole could be intricately entangled with the information inside the black hole, forming a microscopic wormhole connection that preserves the information link. Even as the black hole evaporates, this quantum connection ensures the information is never truly lost. It is transferred and preserved in the correlations between the radiated particles. This paints a picture of a universe that is far more deeply interconnected than we ever imagined, where spacetime itself is woven together by a web of quantum information, creating a self-correcting network that prevents any data from being deleted. The resolution of the black hole information paradox is more than a technical fix for a physics problem. It is a powerful testament to a cosmos that zealously guards its history and structure, ensuring that every bit of information, from the birth of a star to the pages of a book, is forever part of its eternal, consistent fabric. If we could step outside our local galaxy cluster and view the universe from a truly cosmic perspective, we would not see a random scattering of galaxies. Instead, we would witness an architecture of breathtaking grandeur and complexity, a vast, three-dimensional spiderweb of light and matter stretching across billions of light years. This is the cosmic web, the largest known structure in existence, and its formation is a masterclass in cosmic self-organization. It consists of immense filaments or threads of galaxies twisting through space, connecting at dense nodes where massive galaxy clusters reside, all surrounding enormous, empty regions known as cosmic voids. This is not a static sculpture, it is the dynamic, evolving skeleton of the cosmos, and its existence points directly to a universe with a powerful innate tendency to structure and correct the distribution of matter on the grandest of scales. The story of this web begins not with the galaxies themselves, but with something invisible and mysterious: dark matter. In the early universe, dark matter, which interacts only through gravity and not through light, began to clump together first. Tiny quantum fluctuations in the primordial soup, imprinted during the inflationary epoch and visible in the cosmic microwave background, provided the seeds. Regions that were ever so slightly denser had a bit more gravitational pull, slowly attracting more and more dark matter from their surroundings. Over hundreds of millions of years, this process snowballed, building a vast, invisible scaffolding of dark matter filaments and halos. This dark framework is the true backbone of the cosmic web. The glittering galaxies we see are merely the visible tracers, the lights on this hidden highway, forming where the dark matter is most concentrated. But how did this dark matter scaffolding grow so intricate and web-like? The answer lies in the relentless, correcting force of gravity and the counterbalancing influence of dark energy. Supercomputer simulations, such as the famous Millennium simulation, have been instrumental in revealing this process. Scientists program the initial conditions of the universe based on the tiny fluctuations we see in the CMB, and then let the laws of physics play out in a virtual cosmos over billions of years of simulated time. The results are stunningly beautiful and match our observational maps of the universe almost perfectly. They show gravity acting as a universal architect, pulling matter into filaments and nodes. Meanwhile, dark energy acts as the cosmic regulator. As the universe expands, dark energy's repulsive effect becomes dominant, causing the expansion to accelerate. This acceleration effectively puts a brake on the growth of the very largest structures. It prevents the entire cosmic web from collapsing under its own gravity into one gigantic supercluster, preserving the delicate balance between the dense filaments and the vast, empty voids. It's a dynamic tension between two opposing forces, gravity pulling matter together to build structure, and dark energy pushing space apart to limit its growth, together creating the complex, web-like pattern we observe. This self-organizing process is a spectacular example of a feedback loop operating across cosmic time. The initial conditions were set with incredible precision. The fluctuations were there, but they were minuscule. The universe then took those tiny seeds and, through the simple, unwavering application of physical laws, amplified them into the magnificent structure we see today. It's a correction of distribution, a constant sorting and sifting of matter into an orderly, albeit complex, arrangement. The cosmic web is the universe's way of efficiently managing its resources, creating highways of matter where galaxies can form, evolve, and interact, while the voids remain largely empty, their matter having been drained away to feed the growing filaments and clusters. This isn't chaos, it is a deeply structured, self-correcting system that has been evolving for nearly 14 billion years, a testament to a universe that naturally tends toward intricate patterns of order, even on scales so vast they defy human comprehension. Just when we think we've grasped the universe's rules, it reveals a layer of connection so profound it shatters our conventional understanding of space and time itself. This brings us to one of the most mystifying and beautiful patterns in all of physics, the phenomenon of quantum entanglement. Imagine two particles born from the same quantum event, perhaps two photons emitted from a single atom. These particles are then sent flying off in opposite directions, traveling for years, even across galaxies, until they are light years apart. According to all the laws of classical physics, they should now be completely independent entities, their fates unlinked. But the quantum world operates by a different script. These two particles remain intimately linked, their identities fused into a single, shared quantum state. They are entangled, and when you measure a property of one, say, its spin or polarization, its distant partner instantaneously assumes a corresponding state, no matter the immense distance between them. This connection, this instantaneous correction of one particle's state to match the measurement of the other, happens faster than light could ever hope to travel between them. It's as if the universe, at its most fundamental level, refuses to acknowledge separation, maintaining a silent, instantaneous line of communication that defies everything we thought we knew about locality and causality. This spooky action at a distance, as Einstein famously called it, was deeply unsettling to the founders of quantum mechanics because it seemed to violate a core tenet of his theory of relativity, that nothing, not even information, can travel faster than the speed of light. It suggests a form of influence that is non-local, meaning it operates outside the confines of space-time as we experience it. For decades, physicists debated whether this was a real phenomenon or if the particles perhaps carried hidden instructions from the moment they were created, like a pair of gloves separated into two boxes. You know, if you find a left-handed glove in your box, the other must contain the right. But in the 1960s, physicist John Bell devised a brilliant mathematical theorem to test this. His inequalities provided a way to distinguish between a universe with hidden local variables and one with true, spooky quantum entanglement. When the experiments were finally conducted, the results were clear and decisive. They violated Bell's inequalities, proving that the connection between entangled particles is real, instantaneous, and truly non-local. There are no hidden gloves. The universe is far stranger. The act of measurement on one particle doesn't just reveal a pre-existing state. It actively participates in defining the state of its partner, no matter how far away. This isn't a signal being sent. It's a fundamental unity expressing itself across apparent separation. What does this mean for our picture of a self-correcting universe? Entanglement acts as the universe's ultimate mechanism for maintaining cosmic consistency. It's a form of correlation that operates beneath the surface of space-time, ensuring that the properties of particles that were once together remain in a harmonious relationship. This isn't just a curious feature of a few exotic particles in a lab. It appears to be a ubiquitous feature of reality. The vacuum of space itself is thought to be a seething ocean of entangled particles constantly popping in and out of existence. Some theories even suggest that the very fabric of spacetime may be woven together by a vast cosmic web of quantum entanglement. In this view, the connectivity we see in the cosmic web of galaxies might have its roots in this deeper, quantum-level connectedness. Entanglement provides a way for the universe to know itself, to keep its distant parts in sync without the need for any slow, plodding communication through space. It is a silent, instantaneous correction of states, a constant process that maintains a holistic balance across the entire cosmos, ensuring that the whole remains consistent, even if the parts appear wildly separated. This profound interconnectedness challenges the very notion of isolated objects. It points toward a reality that is fundamentally holistic, where what we perceive as separate entities are actually just localized expressions of a deeper, unified whole. The universe, through entanglement, demonstrates that its true nature is one of relationship and connection, not isolation. It constantly works to preserve the correlations born from shared history, refusing to let distance break the bonds it creates. This isn't magic, it's a property as fundamental to the cosmos as gravity or electromagnetism. It suggests that the universe is not a collection of independent things, but a single, intricately connected system that is constantly regulating itself, ensuring that its underlying unity is never lost, no matter how vast and seemingly disconnected it becomes. This silent, instantaneous dialogue between entangled particles is perhaps one of the strongest hints that the cosmos is indeed a self-correcting, self-regulating entity, maintaining its coherence through a web of connection that transcends space and time. This remarkable fine-tuning of our planet's position is far more than a fortunate cosmic accident. It reflects a deeper, more universal pattern emerging from our exploration of other star systems. The concept of the habitable zone, often poetically called the Goldilocks zone, describes the narrow orbital region around a star where the energy output is just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. This isn't a fixed distance, it's a dynamic belt that shifts depending on the star's size, temperature, and lifespan. For a massive, blazing blue star, this zone would be pushed far outward. For a small, cool red dwarf, it would be drawn in very close. Earth's perfect placement within our sun's habitable zone is the first clue. but the real evidence for a cosmic tendency comes from the thousands of exoplanets we've now discovered. With powerful telescopes like Kepler and TESS, astronomers have been cataloging worlds around other suns, and the data reveals something extraordinary. A significant fraction of star systems appear to have planets orbiting within their own calculated habitable zones. We've found rocky, Earth-sized planets circling in that just right region around stars both similar to and vastly different from our own. The TRAPPIST-1 system, for instance, is a compact family of 7 Earth-sized worlds orbiting a cool red dwarf star. Several of these planets reside snugly within the star's habitable zone, suggesting conditions that could allow for liquid water. Another famous example is Proxima Centauri b, a planet in the habitable zone of our very nearest stellar neighbor. While the existence of liquid water doesn't guarantee a habitable environment, factors like atmosphere, magnetic fields, and planetary geology are crucial. The sheer prevalence of these worlds in the right orbital position is statistically compelling. It suggests that the physical processes of planet formation naturally produce a wealth of real estate in these life-friendly orbital bands. The universe, it seems, is prolific in creating opportunities for life, not just in our solar system but across the galaxy. This points toward a form of astronomical self-correction, the chaotic process of planetary system formation, from the swirling protoplanetary disk of gas and dust to the gravitational dance of emerging planets, appears to have a built-in bias toward stability and equilibrium. While planetary migrations can be violent, often flinging worlds into their star or out into interstellar space, the systems that survive over billions of years tend to settle into stable configurations. Planets often find themselves in resonant, non-interfering orbits, and a significant number end up in that temperate zone where water can persist. It's as if the dynamics of solar system evolution possess a filtering mechanism, weeding out the most unstable arrangements and favoring those that can maintain long-term order, including the possibility of clement conditions. This isn't a guided process, but a natural outcome of physics and probability that consistently generates environments where the complex chemistry of life could, in theory, begin. The abundance of habitable zone planets is a powerful argument that our place in the cosmos is not uniquely privileged, but part of a broader, repeating pattern, a universe that seems almost predisposed to creating niches where life could potentially take root and flourish. Our planet's atmosphere feels like a permanent and secure blanket, a given part of our existence, but this fragile layer of gas is under constant assault from the void. Streaming from the sun at nearly 1,000,000 miles per hour is the solar wind, a torrent of high-energy charged particles, mostly protons and electrons, that would, if it struck our atmosphere directly, slowly but surely strip it away, leaving our world a barren, irradiated rock. Yet, we are blissfully unaware of this cosmic bombardment because Earth possesses a powerful, invisible shield, its global magnetic field. This is not a static barrier but a dynamic, living force field, generated deep within our planet by the churning of its molten iron core. This self-sustaining system, known as the geodynamo, acts as a planetary scale corrective mechanism, a perfect example of how the universe builds protective systems to shelter and preserve the islands of complexity it creates. The process that brings this magnetic shield to life is as magnificent as it is complex. At the heart of our planet, the inner core is a solid ball of iron and nickel, under such immense pressure that it remains solid despite temperatures exceeding those on the surface of the sun. Surrounding this solid inner core is an ocean of molten iron, swirling and flowing in colossal convection currents as heat from the inner core radiates outward and the entire Earth rotates. This combination of extreme heat, conductive liquid metal, and planetary spin creates a natural electrical generator of unimaginable scale. Moving a conductive material through a magnetic field generates an electrical current, and conversely, an electrical current generates a magnetic field. This feedback loop, where the motion of the molten iron sustains and amplifies the magnetic field, and the magnetic field in turn influences the motion of the iron, is a self-exciting dynamo. It is a perpetual motion machine powered by the planet's own internal heat and rotation, constantly correcting and regenerating our protective shield against the relentless forces of space. Without this internal engine, the magnetic field would have faded billions of years ago, and Earth's story would have been vastly different. The field itself extends thousands of miles into space, forming a vast protective bubble around our planet called the magnetosphere. When the charged particles of the solar wind encounter this magnetic barrier, they are deflected around Earth, much like water flowing around the bow of a ship. Some of these particles do become trapped, funneled by the magnetic field lines toward the poles, where they collide with atmospheric gases and create the breathtaking auroras, the northern and southern lights. These dazzling light shows are not just beautiful, they are a visible testament to our magnetic field doing its job, harmlessly dissipating this captured energy in a spectacular display. More critically, the magnetosphere prevents the solar wind from directly eroding our atmosphere. We see the tragic alternative on Mars. The red planet, once warmer and wetter with a thicker atmosphere, lost its global magnetic field as its smaller core cooled and solidified. Without that protective shield, the solar wind has, over billions of years, stripped away most of its atmosphere, leaving it the cold, desolate world we see today. Earth's magnetic field is thus more than a shield. It is a guardian of an entire planetary environment, actively maintaining the conditions necessary for its biosphere to thrive. This pattern of magnetic protection is not unique to Earth. It is a recurring theme throughout the cosmos, a universal tool for environmental regulation. Jupiter, the solar system's giant, possesses a magnetic field so powerful it dwarfs our own. If it were visible to the naked eye, it would appear larger than the full moon in our sky, even from Earth. This immense field protects not only Jupiter itself, but also its large, icy moons. Europa, for instance, orbits within Jupiter's magnetosphere, and while the moon's surface is bombarded by radiation, its magnetic interaction with Jupiter may actually contribute to the internal heating that keeps its subsurface global ocean in a liquid state, a potential habitat for life. Even our Sun has a magnetic field which shapes the entire heliosphere, the giant bubble carved out in interstellar space by the solar wind. On a smaller scale, Mercury, despite its small size and slow rotation, retains a weak global magnetic field, likely generated by a partially molten core, which offers it some small protection. And intriguingly, evidence from Mars suggests it may have had a strong magnetic field in its distant past, which faded as its interior cooled, leading to the catastrophic loss of its atmosphere and water. This cosmic recurrence tells us that magnetic fields are a natural and common outcome of planetary physics, a self-regulating feature that arises from the basic ingredients of a molten, metallic core and rotational energy. The universe, it seems, has a preferred method for safeguarding its most interesting real estate, using the dynamo effect to create persistent shields that deflect chaos and preserve the delicate conditions that allow for richer, more complex systems to evolve and endure. The idea of a universe with a single, definitive beginning and a lonely, cold end has long captivated and troubled scientists and philosophers alike. But what if our cosmos is not on a one-way trip to oblivion? What if, instead of a final heat death, the universe is engaged in an eternal dance of death and rebirth, a cycle of renewal that stretches across timelines so vast they defy human comprehension. This brings us to the 18th compelling pattern, cosmic cycle theories, which propose that the universe undergoes endless epochs of expansion and contraction, with each grand cycle acting as a cosmic reset, correcting the imbalances and dissipating the entropy of the previous one to begin anew. This vision presents a cosmos that is not merely self-correcting but truly eternal and self-renewing, a system that avoids both the fiery Big Crunch and the silent heat death through an endless process of cosmic rejuvenation. The most prominent of these models is the conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. In this breathtakingly elegant model, the distant, cold future of our universe does not mark an end but a transformation. As the universe expands forever, accelerated by dark energy, all matter eventually decays or is pulled apart, and even black holes evaporate via Hawking radiation. What remains is a universe devoid of structure, containing only low-energy photons drifting through an vast, empty spacetime. In this featureless state, the universe loses all sense of scale. There is no way to distinguish something large from something small, or a long time from a short one. Penrose posits that at this point of maximum entropy and timelessness, the universe can conformally rescale itself. It can be mathematically transformed to look identical to the hot, dense, small state of a new Big Bang. In this model, the infinite future becomes the singularity of a new eon, a new cycle of creation. The profound implication is that our Big Bang was not the absolute beginning, but simply the continuation of a previous cosmic cycle, with each eon inheriting a clean slate, its entropy effectively reset to zero at the moment of transition. This is the ultimate corrective mechanism. The universe uses its own eventual emptiness and uniformity as the raw material for a brand new beginning. Another fascinating framework is the ekpyrotic model, which draws inspiration from string theory. This scenario imagines our three-dimensional universe as a membrane, or a brain, floating in a higher dimensional space. In this view, the Big Bang was not an explosion from a singularity, but a colossal collision between our brain and a neighboring parallel brain. The immense energy of this impact ignited the hot, expanding universe we observe today. Following this collision, the two brains bounce apart, stretch, and then are drawn back together by gravitational attraction, setting the stage for the next collision and the next cosmic cycle. This model elegantly addresses the problem of entropy. In the cyclic ekpyrotic universe, entropy does not accumulate from one cycle to the next in a way that would lead to a degradation of the process. Instead, each collision or bang wipes the slate clean, allowing the universe to start each cycle with low entropy and a new opportunity for structure formation. The cycles could continue indefinitely into the past and the future, a never-ending series of cosmic rebounds that constantly correct and renew the entire system. Of course, these grand theories are not without their significant challenges and critics. A major hurdle for any cyclic model is the second law of thermodynamics and the seemingly irreversible rise of entropy. Skeptics argue that if the universe has already undergone an infinite number of cycles, it should have already reached a state of maximum entropy. The fact that we observe a universe with pockets of exquisite order and low entropy is a powerful argument against an eternal past. This is known as the Tolman entropy problem. Proponents of cyclic models, particularly the ekpyrotic scenario, have developed sophisticated responses, suggesting that the dynamics of the bounce itself can naturally dilute the entropy from the previous cycle, effectively resetting the entropy clock each time. The search for observational evidence is another critical frontier. Roger Penrose and his collaborators have pointed to unusual, large-scale patterns in the cosmic microwave background, specifically concentric circles of slightly higher temperature variation, which they argue could be the gravitational imprints of incredibly violent events like supermassive black hole mergers from the eon that preceded our own. These Hawking points are highly controversial and not widely accepted as proof, but they represent a brave attempt to find observational fingerprints of a pre-Big Bang universe. The ongoing analysis of the CMB and the quest to understand the nature of dark energy will be crucial in testing the viability of these cyclic ideas against the standard inflationary paradigm. Whether they ultimately prove to be physically true or remain magnificent thought experiments, cosmic cycle theories offer a profoundly different and inspiring vision of reality. They suggest a cosmos with true longevity and resilience, a universe that has mastered the art of recycling on the grandest possible scale. Instead of a single, linear narrative with a definitive beginning and a bleak end, we are presented with a universe that is potentially timeless and self-sustaining, a phoenix that continually rises from its own ashes. This idea resonates deeply with ancient philosophical and spiritual traditions from around the world, from Hindu cosmology with its cycles of creation and destruction presided over by Brahma, to the Stoic concept of the Great Year. It paints a picture of existence not as a fragile, one-off event, but as an eternal, self-correcting process where collapse is always followed by renewal, and every ending is merely a prelude to a new beginning. In this view, the universe is the ultimate expression of balance and perseverance, an entity that has woven renewal into its very fabric, ensuring that the story of existence never truly has to end. Even the very void of space itself, what we might think of as perfect, absolute nothingness, is in reality a scene of unimaginable frenzy and activity. This is the domain of quantum vacuum fluctuations, a phenomenon so bizarre it challenges our most basic intuitions about reality. According to the principles of quantum mechanics, empty space is not a static, empty stage upon which particles perform. Instead, it is a dynamic, seething foam of potentiality, a place where the very concepts of something and nothing lose their meaning. At the tiniest scales of time and space, pairs of virtual particles and their antiparticles spontaneously blink into existence, borrowing energy from the vacuum for an unimaginably brief moment before annihilating each other and returning the energy, thus obeying the conservation laws over the very short term. This isn't just a theoretical curiosity, it's a fundamental property of the universe, and it acts as a constant, underlying process of self-correction that maintains a dynamic equilibrium at the very foundation of everything. We can actually observe the tangible effects of this quantum froth. One of the most famous demonstrations is the Casimir effect. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a vacuum, just a few nanometers apart. In the empty space outside the plates, virtual particles of all wavelengths can spontaneously appear and disappear. But in the narrow gap between the plates, only those virtual particles whose wavelengths fit perfectly between the plates can pop into existence. This creates a slight imbalance in the quantum pressure. There are more virtual particles pushing on the outside of the plates than on the inside. The result: the two plates are gently but measurably pulled together by the pressure of this nothingness. It's a force generated entirely by the restless activity of the quantum vacuum, a direct observation that so-called empty space is actually alive with transient energy. This effect shows us that the vacuum is not passive but is an active participant in the physics of the universe, constantly adjusting and exerting influence. These quantum fluctuations are not confined to exotic lab experiments. They are the very engine behind one of the most important processes in the universe, radioactive decay. Take an unstable atomic nucleus. According to classical physics, the protons inside are all positively charged and should repel each other violently, flying the nucleus apart. The strong nuclear force holds them together, but there is a powerful energy barrier keeping them confined. So how does a particle like an alpha particle, 2 protons and 2 neutrons, ever escape? The answer lies in a bizarre quantum phenomenon called tunneling, and it's driven by vacuum fluctuations. The particle doesn't have to go over the energy barrier. Instead, the inherent uncertainty of the quantum world, fueled by the vacuum's energy, allows the particle to have a small but real probability of simply appearing on the other side of the barrier, as if it teleported through. It's as if the constant jitter of the vacuum provides a tiny, probabilistic nudge that allows nature to correct an unstable configuration, transforming one element into another in a process that is fundamental to the life and death of stars and the very composition of our world. Perhaps the most profound connection lies in the relationship between these quantum jitters and the largest scale we know, the expansion of the entire cosmos. You might recall the cosmological constant, that mysterious form of dark energy causing the universe's expansion to accelerate. The most natural candidate for this energy is the vacuum energy produced by these endless quantum fluctuations. Every cubic centimeter of space, according to quantum field theory, should be brimming with this zero-point energy. There's just one colossal problem. When physicists try to calculate how much energy this should contribute to the cosmos, the number they get is absurdly, impossibly large. We're talking about a value that is 10 to the power of 120 times larger than the value we actually observe from our measurements of the cosmic expansion. This is the largest discrepancy between theory and observation in all of science. It means one of two things. Either our understanding of quantum fields is profoundly incomplete, or some exquisite, unknown cancelling mechanism is at work, a form of ultra-fine tuning where different contributions to the vacuum energy perfectly balance out to produce the tiny, non-zero value we see. This cosmological constant problem is arguably the greatest unsolved mystery in fundamental physics, and it suggests that the universe possesses a hidden self-correcting principle that keeps the violent energy of the quantum vacuum in check, preventing it from tearing reality apart at the seams. This incredible balance points toward a universe that is fundamentally self-regulating from the quantum to the cosmic scale. The vacuum fluctuations represent a system in perfect dynamic equilibrium. Energy is constantly being borrowed and repaid. Particles flicker in and out of existence, but the overall books always balance over the appropriate time scales. This isn't a sign of chaos, but of a deeply ordered process that undergirds all of reality. It provides the background hum against which all particle interactions take place. It drives the processes that change elements and power stars, and it may even hold the key to the ultimate fate of the cosmos. The quantum vacuum is the universe's most basic ledger, a ceaseless, bubbling cauldron of creation and destruction that maintains a perfect, zero-energy balance sheet, ensuring that the fabric of space-time itself remains stable and coherent, providing the steady foundation upon which all complexity and ultimately life can be built. From the seething quantum vacuum to the grand cycles of cosmic renewal, we see a universe profoundly invested in maintaining balance. This same exquisite principle finds its most intimate and immediate expression not in distant galaxies or subatomic particles, but right here inside each and every one of us. Every living organism is a walking, breathing testament to self-correction, a miniature universe tirelessly working to preserve a stable internal environment against a chaotic external world. This biological imperative is known as homeostasis, and it represents a stunning parallel to the larger regulatory patterns we see woven throughout the cosmos, a clear demonstration that the drive for balance is a universal constant, operating at every scale of existence. To understand homeostasis is to understand the very essence of life itself. The term, derived from the Greek words for same and steady, describes the countless automatic processes that keep our internal conditions within a narrow, optimal range. It's not a static state of rest, but a dynamic, active process of constant adjustment, a continuous dance of measurement and response. Your body is equipped with a vast network of sensors that act like millions of tiny scientists, perpetually monitoring critical variables such as temperature, blood pH, oxygen levels, water content, and blood sugar. When any one of these sensors detects a deviation from the set point, the ideal value, it sends a signal that triggers a corrective action to bring the system back into balance. This is a classic feedback loop, and it comes in two primary flavors that mirror the push and pull we see throughout nature. Negative feedback is the most common, acting as a stabilizing force. Think of a thermostat in your home. If the temperature drops below the set point, the heater kicks on to warm the room back up. Once the desired temperature is reached, the heater turns off. Your body does the exact same thing. If your core temperature begins to rise, perhaps from exercise or a hot day, negative feedback loops spring into action. Your brain signals sweat glands to produce perspiration, which cools the skin as it evaporates. At the same time, blood vessels near the skin's surface dilate, allowing more blood to flow and release heat. Conversely, if you're too cold, you shiver. Those rapid muscle contractions generate heat, and blood vessels constrict to conserve warmth by reducing blood flow to the skin. The regulation of blood sugar provides another masterclass in negative feedback. After a meal, your blood glucose levels spike. Specialized cells in your pancreas detect this rise and respond by secreting the hormone insulin into your bloodstream. Insulin acts like a key, unlocking your body's cells and allowing them to absorb glucose from the blood, either to use for immediate energy or to store for later. This process efficiently lowers blood sugar back to its normal level. If too much time passes between meals and blood sugar begins to drop, different cells in the pancreas release a different hormone called glucagon. Glucagon signals the liver to break down its stored glycogen and release glucose back into the bloodstream, raising levels to the optimal range once more. This beautiful hormonal push and pull is a perfect self-correcting system, maintaining the fuel supply for your brain and body with remarkable precision every minute of every day. While negative feedback works to maintain stability, positive feedback takes a different approach, amplifying a response to complete a specific process. This is less about maintaining a steady state and more about driving a system to a conclusive endpoint. A powerful example is the process of childbirth. As labor begins, the baby's head presses against the cervix, stretching it. This stretch is detected and triggers the release of the hormone oxytocin. Oxytocin stimulates uterine contractions, which push the baby's head further down, stretching the cervix even more. This increased stretch stimulates the release of even more oxytocin, leading to stronger contractions. This self-amplifying loop continues, growing in intensity until it culminates in the delivery of the baby and the placenta, at which point the loop is broken. Another example is the formation of a blood clot. When a blood vessel is injured, platelets rush to the site and begin to clump together. These activated platelets release chemicals that attract even more platelets to the area, rapidly building a clot until the bleeding is stopped. In both cases, positive feedback takes a small change and magnifies it, creating a swift and decisive corrective action that is essential for survival. The principle of homeostasis extends far beyond the boundaries of a single organism. It is the fundamental organizing principle of entire ecosystems. A mature forest, a coral reef, or a grassland prairie all function as vast, interconnected homeostatic systems. Predators and prey exist in a delicate balance. If the population of a herbivore like deer grows too large, they may overgraze their food sources. However, this increase in prey also supports a larger population of predators like wolves. As the predators thrive and reduce the deer population, the pressure on the vegetation is relieved, allowing it to recover. With fewer deer, the predator population may then decline from lack of food, and the cycle begins anew. This is a classic negative feedback loop operating on a grand scale, preventing any one species from overwhelming the system and ensuring long-term stability. Even the Earth itself can be viewed through this lens. The Gaia hypothesis, proposed by scientist James Lovelock, suggests that our planet's biosphere, the sum of all life, interacts with the physical environment to form a complex, self-regulating system that maintains conditions suitable for life. For instance, over geological timescales, life has helped regulate the composition of the atmosphere and the planet's temperature. The pervasive presence of homeostasis, from the cellular level to the global scale, powerfully demonstrates that the tendency to seek balance is not a curious accident of biology, but a deep, fundamental pattern of a self-correcting universe. Life, in all its magnificent forms, is not separate from this cosmic principle. It is its most vibrant and eloquent expression. When we observe the majestic spiral arms of a galaxy like our own Milky Way, we naturally assume that most of its mass is concentrated where the light is, in the brilliant central bulge and the shimmering disk of stars. This assumption, based on the physics we understand, leads to a clear prediction about how the galaxy should rotate. Just as planets in our solar system orbit more slowly the farther they are from the Sun, tugged by a weakening gravitational pull, stars in the outer reaches of a galaxy should orbit much more slowly than those near the bright, massive core. For decades, this was the accepted model. Then, in the 1970s, astronomer Vera Rubin and her colleagues made a measurement that would shatter this conventional picture and reveal one of the universe's most profound secrets. Using sensitive spectrographs, Rubin meticulously mapped the rotation speeds of stars in the Andromeda galaxy across vast distances from its center. The results were not just surprising, they were revolutionary. Instead of slowing down, the stars in the outer regions were whipping around the galactic center at nearly the same high speed as those closer in. It was as if the entire galaxy, from its core to its farthest fringe, was rotating like a single, solid disk. This was utterly impossible according to the laws of gravity and the visible mass of stars and gas. The only logical conclusion was that there had to be far more mass in the galaxy than anyone could see, an enormous amount of invisible matter whose gravitational influence was dominating the dynamics of the entire system, holding these swiftly moving stars in their tracks and preventing the galaxy from simply flying apart. This discovery of these flat galactic rotation curves was the first direct and undeniable evidence for what we now call dark matter. This invisible substance isn't just a minor component, it is the primary architectural material of the universe. We now understand that dark matter forms vast, diffuse halos that extend far beyond the visible edges of galaxies. These halos are not like clouds of normal matter. They do not emit, absorb, or reflect light, and they barely interact with each other or with regular matter except through the force of gravity. This is why they are invisible, yet their gravitational pull is the cosmic scaffolding upon which galaxies are built. In the early universe, slight density fluctuations in the dark matter distribution provided the gravitational seeds that attracted ordinary hydrogen and helium gas. Without this invisible framework, the gravity from the visible matter alone would have been far too weak to pull itself together against the expansion of the universe in the time available. Galaxies as we know them simply would not have formed. Dark matter acted as the gravitational anchor, the unseen hand that gathered the raw materials and sculpted them into the magnificent structures we see today. The role of dark matter extends far beyond mere formation. It is the essential stabilizing force that maintains galactic integrity over billions of years. Imagine a star racing along the outer arm of a spiral galaxy. According to the visible mass alone, the gravitational grip of the galaxy's core should be too weak at that distance to keep it in a stable orbit. The star should be flung out into the intergalactic void, a lost traveler in the dark. This doesn't happen because that star is not orbiting just the bright core. It is orbiting the entire, massive, and invisible dark matter halo in which the galaxy is embedded. The halo's gravity provides the extra pull, the corrective force that balances the star's high velocity and keeps it securely bound to the galaxy. This is a continuous, dynamic process of gravitational correction happening in every galaxy, a silent, unseen interaction that maintains the beautiful, coherent structures we observe. It is a cosmic balancing mechanism of the highest order, ensuring that these immense islands of stars remain intact for cosmic epochs. This narrative of an unseen corrector is further supported by observations of entire galaxy clusters. When we look at these massive collections of thousands of galaxies, we see that they are filled with extremely hot, X-ray emitting gas. The gravity of the cluster's visible mass is insufficient to hold onto this seething, high-energy plasma. It should have dissipated into space long ago. Yet it remains confined by the immense gravitational well of the cluster's dominant component, its dark matter. Even more dramatic evidence comes from gravitational lensing, where the gravity of a massive object like a galaxy cluster bends the light from more distant galaxies behind it, distorting their images into giant arcs. The amount of bending we see is far greater than what the cluster's visible mass can account for, directly revealing the presence and distribution of the cluster's overwhelming dark matter content. Across multiple lines of evidence, from the rotation of individual galaxies to the dynamics of the largest structures in the cosmos, the message is consistent and clear. The universe is filled with a mysterious, invisible substance whose primary purpose seems to be gravitational regulation. It builds, it shapes, and most importantly, it sustains. Dark matter is the universe's ultimate stabilizer, a hidden framework that actively maintains the structural integrity of the cosmos, ensuring that its beautiful constructions do not unravel but endure for billions of years. In our journey through the cosmos, we've encountered dark matter and dark energy, unseen forces that correct and balance the universe on the grandest scales. But what about the subatomic realm? Could there be a hidden symmetry woven into the very fabric of reality, one that partners every known particle with a secret twin? This brings us to one of the most elegant and ambitious ideas in modern physics, supersymmetry. At its heart, supersymmetry is a proposal for profound cosmic balance. It suggests that for every particle we know of in the Standard Model, every electron, quark, and photon, there exists a hidden super-partner particle. Electrons would be paired with selectrons, quarks with squarks, and photons with photinos. This isn't just about doubling the number of particles. It's about introducing a powerful new symmetry into the laws of physics, a symmetry between the two fundamental classes of particles, fermions, which are the building blocks of matter, and bosons, which are the force carriers. In a supersymmetric universe, these categories are no longer separate. They are two sides of the same coin, deeply interconnected in a dance of perfect correspondence. This idea of balance isn't just mathematically beautiful, it solves some of the most nagging problems in theoretical physics. The most famous of these is the hierarchy problem, which is essentially a question of unnatural fine-tuning. Consider the Higgs field, which gives other particles their mass. The mass of the Higgs boson itself is incredibly sensitive to quantum corrections from its interactions with virtual particles that constantly flicker in and out of the vacuum. These virtual particles include extremely heavy entities, like those predicted by grand unified theories. The calculations suggest these interactions should drive the Higgs mass to a value 1 trillion times larger than what we actually observe, a value that would make atoms, chemistry, and life itself impossible. To get the correct tiny mass we see, physicists would have to artificially and precisely fine-tune the equations to cancel out these enormous contributions, digit by digit, to an almost miraculous degree of accuracy. It's as if you had to balance a pencil perfectly on its tip on a windy day, and it somehow stayed there for billions of years. This degree of unexplained fine-tuning feels deeply unsatisfying. Supersymmetry offers a stunningly elegant way out. In a supersymmetric world, the contributions from virtual fermions and their new superpartner bosons would be exact opposites. They would cancel each other out perfectly and naturally, eliminating the need for any artificial fine-tuning. The universe would automatically correct this quantum instability, protecting the light mass of the Higgs boson through a built-in, balancing partnership between matter and force particles. Beyond this, supersymmetry provides a compelling candidate for the identity of dark matter. The lightest of these proposed superpartners, often called the neutralino, would be stable, electrically neutral, and would only interact weakly with normal matter, properties that perfectly match the profile of the cold dark matter that shapes our cosmos. In this single stroke, supersymmetry could solve two of the greatest mysteries in physics, stabilizing the Higgs mass and revealing the nature of the invisible matter that holds galaxies together. It also offers a crucial step toward the holy grail of theoretical physics, a grand unification of all forces. The strengths of the electromagnetic, weak, and strong forces change with energy. In the standard model, their lines on a graph almost meet but don't quite cross at a single point. Introduce supersymmetry, and those lines elegantly converge, suggesting that at the incredibly high energies of the early universe, these three forces were indeed unified into a single, fundamental superforce. This points toward a universe whose laws are not a collection of separate rules, but a unified, coherent, and balanced whole. The profound implication of supersymmetry is that the universe might fundamentally operate on a principle of partnership and balance. Even at the most microscopic level, reality seems to avoid extremes and instability through a system of checks and balances. For every particle that pushes one way, there is a partner that pulls the other, creating a natural, self-correcting equilibrium. This isn't a law imposed from the outside. It is an inherent property of the mathematical structure of spacetime itself. It suggests that the cosmos has a deep-seated preference for symmetry, a tendency to resolve tension and conflict through the introduction of a complementary counterpart. While experiments at the Large Hadron Collider have not yet found direct evidence for these superpartners, the theoretical appeal of supersymmetry remains immense. It represents a powerful vision of a universe that is not only unified and balanced but also inherently stable, equipped with its own microscopic mechanisms to correct potential imbalances and preserve the delicate conditions that allow for a complex and observable reality to exist. Deep within the heart of a black hole, according to Einstein's theory of general relativity, lies a point of infinite density and zero volume, a singularity. Here, the known laws of physics cease to function. Gravity becomes so intense that space-time itself curves to a point of infinite curvature, and our equations simply break down, offering no predictions and no answers. It is a realm of pure mathematical chaos, a place where cause and effect could become untethered, and the fundamental predictability of the universe might completely unravel. The existence of such a point of lawlessness poses a terrifying threat to the orderly cosmos we observe. If a naked singularity, one not hidden inside a black hole, were to exist, its unpredictable physics could spill out into the wider universe, potentially allowing effects to occur without causes or information to be created or destroyed at will. The very foundation of scientific inquiry, which relies on a stable, consistent set of physical laws, would be shattered. This is where the cosmic censorship hypothesis enters the stage, not as a proven law, but as a profound and compelling conjecture about how the universe might protect itself from its own most extreme creations. Proposed by the renowned physicist Roger Penrose in 1969, this hypothesis acts as a kind of cosmic safety protocol. It suggests that nature possesses a fundamental aversion to naked singularities. The conjecture states that every singularity that forms through the realistic gravitational collapse of a star or other massive object must always be hidden from view, permanently cloaked behind an event horizon, the one-way boundary of a black hole from which not even light can escape. The event horizon, in this view, is not just a fascinating feature of a black hole. It is a crucial containment barrier. It acts as a cosmic firewall, not of energy, but of unpredictability, sealing the infinite madness of the singularity away from the rest of reality, ensuring that its lawless physics remain a prisoner, unable to influence the orderly universe outside. This idea of censorship is a powerful form of cosmic self-correction. It implies the universe has a built-in mechanism to preserve causality, the principle that every effect must have a cause that precedes it. Within the sealed chamber of a black hole, the bizarre physics of the singularity can play out without violating the rules that govern everywhere else. The event horizon ensures that no signals, no information, and no consequences of the singularity's chaos can ever propagate outward to affect distant observers. The universe, in effect, isolates its own worst bugs in a quarantine from which there is no escape, maintaining the integrity of physical law for the entire rest of the cosmos. This isn't an active process like a conscious decision. It's more like a fundamental rule of gravitational construction. The way matter collapses under its own weight seems to always form this protective barrier automatically, correcting for the potential problem of a singularity before it can become a threat to cosmic order. The need for such a censor becomes clear when we consider the alternative. A naked singularity would be a true cosmic anomaly, a place where the predictable fabric of reality frays into nothingness. It could theoretically allow for time travel paradoxes, where an event could cause itself in a loop with no beginning. It might violate the conservation of information, allowing it to be truly created or destroyed. The presence of such an object would make it impossible to predict the future evolution of any region of space that interacted with it, as the laws of physics would literally change from one moment to the next. The cosmic censorship hypothesis saves us from this nightmare scenario. It reassures us that the universe is fundamentally predictable and stable, that the laws we work so hard to uncover are universal and reliable. It suggests that the cosmos is self-regulating, designed in such a way that even its most violent and extreme events, the gravitational collapse of massive stars, result in structures that protect the overall order rather than destroy it. The black hole, often portrayed as the ultimate agent of cosmic destruction, may in fact be one of the universe's most important guardians, a vault that keeps its most dangerous secrets locked away forever. Yet, even if our planet were to face an unimaginable catastrophe, a sterilizing impact or a runaway greenhouse effect that extinguished every last living cell, the story of life in our solar system might not be over. This brings us to a fascinating and controversial idea that suggests biology has a way of enduring beyond the lifespan of any single world. The theory of panspermia proposes that life is not exclusively a product of individual planets, but could be a cosmic traveler, distributed between worlds by asteroids, comets, and interstellar dust. In this view, a planet's biosphere is not an isolated garden but potentially part of a much larger, interconnected ecosystem, with life's raw materials or even living organisms themselves constantly being exchanged across the vast distances between stars. This presents a powerful form of biological self-correction, a mechanism where the universe itself ensures the persistence of life by constantly reseeding and redistributing it, effectively using celestial mechanics as a delivery system to overcome local planetary disasters. The journey for these microscopic interstellar voyagers would be unimaginably harsh, and this is the greatest challenge to the panspermia hypothesis. To travel from one star system to another, any potential life form would have to survive three incredibly demanding phases. First, there's the escape. For material to be launched from a planet like Mars and achieve escape velocity, it must endure a titanic impact event with forces and temperatures that would instantly vaporize most rock. Yet we have tangible proof that this is possible. Right here on Earth, we have discovered over 300 meteorites that were definitively identified as coming from Mars, blasted off its surface by ancient asteroid impacts. The most famous of these, are LH84001, even contain tiny structures that some scientists initially argued could be fossilized nanobacteria, though that interpretation remains hotly debated. The very existence of these Martian rocks on our world proves that material transfer between planets is not just theoretical, it's a fact of our solar system's history. If microbes could somehow survive the initial blast and the violent acceleration into space, the next hurdle is the journey itself. Drifting in the frozen, airless vacuum of space for millions of years, these potential colonists would be bombarded by relentless cosmic radiation and ultraviolet light from nearby stars, which would shred DNA and other complex organic molecules. However, we know that certain extremophile organisms on Earth, like Deinococcus radiodurans, possess incredible repair mechanisms that allow them to withstand colossal doses of radiation. Other bacteria have been revived after millions of years trapped in ice or buried in deep salt deposits, suggesting long-term dormancy in harsh conditions is not impossible. Furthermore, a rock of sufficient size could provide a crucial shield. Its interior could potentially remain a protected refuge, with temperatures stable enough to preserve any dormant passengers for an interstellar voyage. The final test is re-entry and landing. A meteorite screaming through an alien atmosphere experiences tremendous friction, heating its outer surface to incandescent temperatures. But again, physics provides a potential solution. While the exterior of the rock melts and vaporizes, forming a protective fusion crust, the interior can remain surprisingly cool. Experiments have shown that a rocky body several meters in diameter can have a core that never rises above the boiling point of water, a temperature many hardy Earth microbes could easily endure. We've even observed the incredible durability of lichen and bacterial spores when mounted on the outside of the International Space Station, exposed directly to the vacuum of space for years, only to be revived later back on Earth. When you combine these pieces of evidence, the proven transfer of material between planets, the existence of radiation-resistant and dormant life forms, and the feasibility of surviving atmospheric entry, the idea of panspermia transitions from science fiction to a legitimate, albeit unproven, scientific possibility. It suggests that the chemistry of life, and perhaps life itself, might be a far more resilient and widespread phenomenon than we once believed, capable of using the rocky debris of cosmic collisions as makeshift arcs to sail between the stars. If panspermia is a real process, its implications for the universe's character are profound. It would mean that the emergence of life on a planet might not always be a singular, isolated genesis event. Instead, it could be more like the seeding of a field by wind-blown spores. A planet with just the right conditions could be inoculated with the building blocks of life, or even with dormant life itself, delivered by a comet that formed around another star millions of years earlier. This transforms a catastrophic asteroid impact from a purely destructive force into a potential vector for creation and renewal. An impact large enough to cause a mass extinction on one world could simultaneously blast life-bearing rocks out into the solar system, some of which might eventually find their way to another young, habitable planet millions of years in the future, ready to begin the cycle again. This creates a powerful self-correcting mechanism for biology on a galactic scale. Local extinctions, no matter how total, would not be a permanent end. The universe, through the random but constant gravitational interactions of comets and asteroids, would act as a grand disperser of life, ensuring that if it arises anywhere, it has a chance to spread and persist across vast stretches of space and time. It suggests a cosmos that is not only habitable but actively bio-friendly, with physical processes that not only create the conditions for life, but also provide the means for its dissemination and long-term survival, constantly correcting for isolated planetary calamities by offering new worlds as potential homes. Imagine a universe where the true nature of reality isn't three-dimensional at all, but is actually a magnificent cosmic projection, a hologram of staggering complexity. This is the essence of the holographic principle, a revolutionary idea that suggests all the information contained within any volume of space, every star, every planet, every person, is actually encoded on its two-dimensional boundary. Think of it like the security chip on your credit card. That tiny, flat strip holds all the information needed to represent your financial identity in the digital world. In a similar but infinitely more profound way, the holographic principle proposes that the entire three-dimensional universe we experience might be a projection from information stored on a distant, two-dimensional surface. This isn't just a wild speculation. It's a serious theoretical framework born from the fiery clash between general relativity and quantum mechanics, and it points toward a universe that manages its information with ultimate efficiency, acting as a self-correcting system at the most fundamental level. The roots of this astonishing idea lie in the depths of a black hole and the infamous information paradox. When something falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. But Stephen Hawking discovered that black holes aren't completely black. They slowly evaporate by emitting radiation. The problem was that this Hawking radiation appeared to be completely random and thermal, carrying no information whatsoever about what had been consumed. This implied that the information about the stuff that fell in was permanently destroyed, a direct violation of a core tenet of quantum mechanics. That information must be conserved and can never be truly lost. The universe, it seemed, had a glaring bug in its operating system. The holographic principle emerged as the most elegant solution. It was inspired by the work of physicist Jacob Bekenstein, who found that the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. This was a bizarre and counterintuitive result. We expect the capacity of a container to be related to how much it can hold, its volume, not the area of its walls. This discovery hinted that the event horizon wasn't just a barrier, it was a data storage device. The information about everything inside the black hole wasn't lost in the singularity. It was meticulously encoded on the event horizon's two-dimensional surface. As the black hole emits Hawking radiation, it isn't just random noise. It's a complex process that carefully reads and transmits this encoded information back out into the universe, preserving it perfectly and resolving the paradox. The black hole acts as a cosmic hard drive that never truly deletes data, only reformats and releases it, showcasing a profound mechanism of information conservation. This principle was catapulted from a black hole curiosity to a full-fledged model of the universe by the work of physicist Juan Maldacena. In 1997, Maldacena proposed a specific, mathematically rigorous realization of holography, known as the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. This mouthful describes a breathtaking duality. A gravitational theory operating in a hypothetical warped space can be perfectly described by a quantum field theory without gravity operating on its lower dimensional boundary. It's like having a detailed, three-dimensional video game world that is completely generated and defined by the code written on a two-dimensional disk. The code on the boundary, the CFT, contains all the information needed to create the entire universe, the ADS space, within it. While our actual universe isn't exactly an anti-de Sitter space, the power of this duality is its proof of concept. It demonstrates that holography isn't just a metaphor, it is a mathematically consistent way that a universe could operate. It suggests that gravity and the three-dimensional world we perceive might not be fundamental, but could emerge from a more basic, two-dimensional reality where there is no gravity at all, only quantum information interacting on a vast cosmic surface. The implications of this for a self-correcting universe are staggering. If the holographic principle is true, then the cosmos is the most efficient information processing system imaginable. It doesn't waste resources storing data in a bulky three-dimensional format. It compresses it onto a two-dimensional surface, optimizing its structure for maximum efficiency. This provides a powerful mechanism for cosmic self-regulation. Any potential paradox or inconsistency that might arise within the three-dimensional world, like the information loss in a black hole, is automatically resolved at the deeper, two-dimensional level where the laws of quantum mechanics reign supreme and information is always preserved. The three-dimensional universe is a projection, a shadow, and the true master code exists on the boundary, constantly maintaining consistency and order. This holographic view unifies the two great pillars of physics in a beautiful way. The strange, probabilistic world of quantum mechanics, which governs the very small, finds its home on the boundary. The geometric, space-time warping world of general relativity, which governs the very large, emerges from it in the bulk. They are not two separate, conflicting theories. They are two complementary descriptions of the same reality, seen from different perspectives. The universe, in this light, is a self-optimizing, self-correcting hologram, ensuring its own logical consistency by encoding its entire history and structure on a distant, two-dimensional film, a cosmic Rosetta Stone that holds the key to understanding everything. But if the holographic principle suggests our entire universe is a projection from a two-dimensional boundary, a kind of cosmic information processing system, it forces us to ask an even more profound question: what lies beyond the code? What is the nature of the reality that contains this cosmic hard drive? This brings us to the final and perhaps most expansive pattern in our exploration, the multiverse. The concept of a multiverse is the ultimate expression of cosmic self-correction, a framework where our universe is not a singular, lonely entity, but merely one page in an infinite library of universes, each with its own unique set of physical laws and constants. In this grand vista, the astonishing fine-tuning we observe is not a miracle requiring a designer, but the inevitable outcome of a natural selection process operating on a cosmic scale. We find ourselves in a universe that allows for our existence precisely because we couldn't find ourselves anywhere else. The most compelling version of this idea emerges directly from the theory of cosmic inflation. As we discussed earlier, inflation proposes a period of hyper-fast expansion in the universe's first moments, but many physicists, including its original architects, believe this inflation may not be a one-time event that started and stopped everywhere. Instead, it could be eternal. The idea is that the inflationary field, the energy that drove the rapid expansion, doesn't disappear all at once. In most regions, it decays, ending inflation and allowing for a hot Big Bang and the formation of a universe like our own. But due to quantum fluctuations, other regions of spacetime continue to inflate at an exponential rate. This creates a mind-bogglingly vast and ever-growing mosaic of pocket universes, or bubble universes, all embedded within a forever inflating megaverse. Each of these bubbles is a separate universe, causally disconnected from all the others, and each one could have a different set of physical laws emerging from the random way the inflationary field decayed within it. In some bubbles, the strength of gravity might be 1 billion times stronger. In others, the electromagnetic force might be too weak to hold atoms together. The vast majority of these universes would be stillborn, chaotic, or utterly barren, incapable of supporting any form of complexity. But in a near-infinite array of possibilities, a tiny fraction of bubbles will, by pure chance, have the exact right combination of constants to allow for stars, planets, and life. Our universe isn't fine-tuned, it's just the one we won in the cosmic lottery. This elegantly reframes the anthropic principle from a philosophical curiosity into a powerful explanatory tool. The reason we observe such perfect conditions isn't because they were chosen for us, but because we are a product of those conditions. It's a cosmic version of the observer effect. Imagine a puddle of water waking up one morning and thinking, "This hole I'm in is perfectly shaped for me. Its contours match my edges exactly. It must have been designed just for me to sit in." The puddle doesn't realize that it's the one that conformed to the shape of the hole, not the other way around. In the same way, we are the puddle. We conform to the universe we find ourselves in. The multiverse theory provides the landscape of countless holes, and we simply exist in one that fits. This is self-correction through sheer statistics. The universe doesn't need to actively adjust its parameters. It simply generates every possible parameter set, and only the stable, life-permitting configurations ever get observed. The process is blind, automatic, and incredibly wasteful, but within a truly infinite multiverse, every possible outcome, no matter how improbable, will happen somewhere, sometime. This idea finds powerful support in string theory, a leading candidate for a theory of everything. String theory suggests that the fundamental building blocks of reality are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of the particles we see. But for the mathematics to work, string theory requires extra spatial dimensions beyond the 3 we experience, often 6 or 7 more, curled up into shapes known as Calabi-Yau manifold. The catch is that there are a staggering number of possible ways these dimensions can curl up, perhaps 10 to the 500 or more. Each different configuration results in a different vacuum state, which dictates the laws of physics for that universe, including the values of constants like the cosmological constant and the mass of the electron. This landscape of possible universes is so vast that it effectively guarantees that every conceivable set of physical laws will be realized in some universe within the multiverse. Our universe, with its specific, life-friendly laws, is just one point in this incomprehensibly vast landscape. The multiverse, therefore, is not a single theory but a natural consequence of several of our best physical theories: inflation, quantum mechanics, and string theory, all pointing toward a reality far grander and more populous than we ever imagined. It represents the ultimate expression of a self-correcting cosmos, not by fine-tuning a single universe, but by creating a framework so expansive that every possible tune is played, and we are simply here to hear the one beautiful melody that allowed for our existence. After journeying through 26 distinct and astonishing patterns, from the fine-tuning of fundamental constants to the mysterious dance of quantum entanglement, a breathtaking tapestry begins to emerge. These aren't isolated curiosities or a simple list of cosmic coincidences. Instead, they appear as different facets of a single, profound truth. The universe operates with an inherent tendency toward balance, regulation, and the preservation of complexity. It's as if we've been examining the individual gears, springs, and levers of a magnificent clock, and now we can finally step back to see the entire mechanism working in harmonious synchrony. The most striking revelation is how this self-correcting behavior manifests across every conceivable scale. In the subatomic realm, quantum decoherence and the measurement problem show particles resolving their fuzzy potential into definite reality through interaction. Zooming out, biological evolution demonstrates life's relentless drive to adapt and perfect its fit within a changing environment. On a planetary scale, magnetic fields and orbital resonances provide stability for billions of years. And at the very largest scales, dark energy and cosmic inflation act as cosmic thermostats, fine-tuning the expansion and structure of the entire cosmos. This isn't a hierarchy but a holographic-like principle where the same theme of dynamic equilibrium repeats itself, from the very smallest to the very largest systems we can observe. Several powerful, unifying themes weave through these diverse patterns, acting as common threads in the cosmic fabric. The first and perhaps most fundamental is the principle of conservation. We see it in the black hole information paradox, where the universe seems to possess a fundamental law that information can never be truly lost, only transformed. We see it in galactic recycling, where the death of stars seeds the birth of new ones, conserving the complex elements necessary for planets and life. This drive to conserve information, energy, matter, and structure is a primary engine of cosmic correction. A second theme is the pursuit of equilibrium, though not a bland and static one. This is a dynamic, active equilibrium. Homeostasis in living organisms maintains a steady internal state by constantly expending energy. The solar system's orbital stability is not a perfect, motionless arrangement, but a complex gravitational dance of resonances and adjustments. Even the cosmic web represents a dynamic balance between the gravitational pull of matter and the repulsive push of dark energy. The universe seems to favor stable, sustainable states that can persist over astronomical timescales. A third unifying theme is adaptation and response. The universe is not a static set piece. It is a dynamic system that responds to changes and challenges. Biological evolution is the most clear-cut example, where random mutations are filtered by environmental pressures to create exquisite adaptations. But we see a similar principle in the cosmic censorship hypothesis, where the laws of physics themselves seem to adapt to contain the chaotic threat of a naked singularity, preserving causality for the rest of the cosmos. The anthropic principle can be viewed through this lens as well, a form of cosmological adaptation where the parameters of reality are such that they allow for observers who can respond to and interact with their environment. This capacity for response implies a universe that is not predetermined in every detail, but one that contains within it the potential for feedback, learning, and creative change. These themes together paint a picture of a cosmos that is far more resilient, sophisticated, and interconnected than a mere collection of particles obeying rigid laws. They suggest a universe that is, in a very real sense, a participatory system, from the quantum level where observation seems to play a role in defining reality, to the biological level where life actively shapes its planetary environment. The act of interaction itself appears to be a key part of the corrective process. We are not passive observers of a clockwork universe, but potentially active participants in a self-regulating, self-aware cosmos, engaged in a continuous dance of co-creation that has been unfolding for nearly 14 billion years. Our journey through these 26 astonishing patterns reveals a cosmos that is far more than a collection of random parts chaotically colliding. What emerges is a picture of a deeply integrated, self-regulating system, a universe that appears to possess an innate and sophisticated tendency to seek balance, preserve information, and foster complexity against all odds. From the impossibly precise values of the fundamental constants that allow atoms to exist, to the self-perpetuating dance of galactic recycling, from the quantum vacuum's frenetic energy to the conscious observation that seems to crystallize reality itself, we find a consistent theme. The universe is not a static stage but a dynamic participatory process, constantly adjusting, refining, and correcting itself across every scale of existence. This isn't a suggestion of a conscious designer in a traditional sense, but rather a compelling argument for a reality whose very laws and mechanisms are inherently biased toward creating and sustaining order. While the how remains one of science's greatest frontiers, the that is increasingly difficult to ignore, the evidence points toward a cosmos that is resilient, adaptive, and strangely consistent. Whether through the brutal filter of a multiverse, where only self-consistent universes can be observed, or through some deeper, yet-to-be-discovered principle of self-organization, the outcome is the same. We find ourselves in a universe that is remarkably well-suited for the journey from chaos to consciousness. This journey suggests that we are not merely passive spectators in a predetermined cosmic play. The participatory nature of quantum mechanics, the adaptive drive of evolution, and the very act of our observation and inquiry hint that we may be active agents in this ongoing process of cosmic self-correction. Our quest for understanding, our drive to explore these mysteries, might itself be a part of the universe's way of knowing itself, of refining its own narrative. This realization invites a profound shift in perspective. It encourages us to see ourselves not as separate from the universe, but as an expression of it, a localized part of the cosmos that has become aware and is now beginning to comprehend its own origins and underlying nature. The boundaries between the observer and the observed, between the living and the non-living, between the quantum and the cosmic, begin to blur into a single, magnificent story of a reality that is both creative and consistent, both chaotic and orderly.